People of Earth, what is happening? How's everybody doing? We are gathered here today for an incredible conference. Let's just be honest. We've got the best and the brightest minds in their field coming on here to talk to us mere mortals about what they're doing to advance the operational ML space. I'm excited. I don't know about y'all. Let me know. Tell us in the chat. You guys pumped for this? Women, men, everyone, people, we could call it. So I want to prepare you for a few things that we're about to experience in these next couple hours. And first thing I will warn you to be prepared for is the amount of diagrams that you are about to see. We're going to see a lot of diagrams coming up here, so be prepared for that. Next up, I want to let you know, we're going to hear a lot of filler words. I said they were the best and brightest minds in their field, but that doesn't mean you're not going to hear some ums, ahs, kinda, sorta, likes, you name it. We're going to hear them. And last but not least, be prepared because I am about to give away so much swag that it is going to seem like a joke. All right. So now, let's just be honest. When we're talking about swag, what better way is there to spend your money that you just got from a $300 million funding round for your Series E and slap your logo onto a picnic blanket and then give it away to some random strangers that were talking in a free virtual conference? That is just beauty in my eyes. So how can you get some of this swag? Well, I've got that all worked out for you. There's some logistical things you need to know. One is that we are in Slack. If you are not in Slack already, that's where it's all going down. Jump into Slack and let yourself be known because you're probably going to increase your odds of getting some swag. And all of the speakers, after their talks, they're going to be answering questions in Slack. Next up, for a little announcement, in case you missed it, about the next event that is happening, the next apply. This is like right now what we're doing. It's like a pregame. We're having this half-day event. It's awesome. We've got incredible speakers. And then in May, there is going to be a 2-day event. So get ready for that. If you're not already registered, I highly recommend going and registering now because that is going to be another killer event. Next up, I want to thank our sponsors. And we've got some incredible sponsors that all be sharing all of their logos and all of that good stuff next in when we talk about this swag and we get to see who's given swag and who some of the partners were. But we just got to give a shout out to all of them. And last but not least, we do have a Twitter hashtag. If you would like to tweet at us, that is #ApplyConf. And all of these sessions that you're seeing now, including me and this intro, it's all going to be available for on-demand viewing after the fact. So if you got to go out and pick up your kids from school or whatever you may have to do, we got you covered. And before you ask that in the chat for the millionth time, yes, I think we all know by now it's been a long pandemic. We have gotten used to virtual events and we understand. Without further ado, I want to bring up our first keynote speaker. And I'm going to just paging Mike Del Balso. Is he around? This is the guy. There he is. There he is. Mike Del Balso, aka that Michelangelo guy, aka the one reason that we can't stop hearing about feature stores. I hear you got to talk for us, Mike.
Yes. Yeah, I do. We can go through that. Thanks for the intro, D. I appreciate it. Thanks for hosting today. This is great.
No problem, man.
A lot of everybody is hoping that we're going to get another couple of songs throughout the day, maybe a meditation session or something like that.
Mm-hmm. We definitely will be. And I brought my ukulele this time.
Oh, perfect.
So,
okay.
Yeah.
Cool. Well, okay. Well, thanks, Dee. So, hi everybody. Thank you. Thanks for joining Apply. We do a couple of these per year. We have a much bigger event in May, so just as Dee said, make sure to go sign up for that right now. That's something that we're super excited about as well. But today, I just kind of want to talk about a variety of challenges we see when people are building features, and why some of the data engineering is not as easy as it is when putting machine learning into production. And that's kind of the theme that I've got for my short talk today, but there's a lot of different talks around putting ML into production and the practical and applied challenges of doing that. So stick around all day. Okay, so I'll pull up some slides here. Okay, cool. And briefly, let me just introduce myself. So I'm Mike. I'm one of the co-founders of Tekton, and I'm the CEO at Tekton. And as Dee mentioned, I previously worked at Uber and helped build the Michelangelo system that is kind of the internal ML platform at Uber. But today we're talking about a variety of features that are found in the wild, and how teams can practically manage them well. So we'll go through kind of some intuition behind solving these prediction problems. We'll go through an operational machine learning example, some common feature types that we see, and then some realistic constraints that make it challenging to actually to build the ideas that we have from these features, and then a better way to handle those constraints and get around these constraints. So firstly, modeling problems, right? So let's say we're trying to predict cardiovascular disease. That's right up here. This is a causal graph. So this every arrow on this graph represents an arrow from X to Y, represents X affects Y in some way. And so you can imagine tendency to work online has an effect on immobility, has an effect on obesity, has an effect on your susceptibility to get cardiovascular disease. This tries to be a more accurate model of the full causality of a problem like this if we're trying to understand cardiovascular disease. When we do in machine learning, we don't tend to go this far. You always hear start simple. And so we might actually, if we're just taking a first crack at this, we might start with something like this. Okay, so this is based on intuition, get some signals from about obesity, bad diet, how much physical activity does this person have? Is there any immobility? These are things that intuitively may affect the risk of cardiovascular disease. And of course, we may have different data sources for this, and we've got to turn these into specific features. So we don't necessarily know the relationship between the mechanism between a bad diet, and cardiovascular disease. But we're hoping our model will figure that out. And so, what our challenge is to get the right signals to be available for our model so it can learn that. So let's take a lot more like operational ML example, something that you would actually put into your, build into your product, right? So let's imagine we are a payment processor, and our customers are e-commerce companies, and when someone's checking out on their website, we're processing that payment. We're giving the money to the e-commerce company and telling them to send the product to the customer. A big thing that happens here is fraud. And so a big prediction that we have to make is, how likely is this to be fraudulent? How likely is it that someone has hacked into this account, stolen this credit card, whatever it is? Because we have to either accept the purchase or deny the purchase. And so there's a variety of different things that we can take into account when making that prediction, right? We have a couple of things. Transaction context. This is stuff we can see right now about this transaction. User context. This is stuff about the user, where they logged in, stuff like that. User history, what do we know about this user in the past? And then other activity that we see across the website. And so this is not really enough to just directly put into an ML model. We typically need to kind of get a little bit more intuition about like what about these data sources are relevant for us to make a prediction. And so let me see my slide here. There we go. So we're probably trying to get a kind of sense out of this data of, how unusual is this purchase? How normal does this user look right now compared to other users or compared to how they normally look? Also, historically, like, did this user have suspicious behavior in the past? And then kind of as like a right now type of thing, is there a lot of weird behavior across the website right now? Is there, very recently, have we seen an increase in fraud? That might help us better understand or better predict if there is, if this particular transaction is likely to be fraudulent. But even this is not fully, this doesn't get us all the way there. We need to actually get very concrete with specific features. And so we might do something like this. Is this transaction abnormally large? Is the user logged in from a specific location? Has this user been flagged for fraudulent activity? These are things that you can directly turn into a SQL query or some specific feature transformation. Has there been an abnormally large number of similar transactions that we've observed in the past few minutes? That's a really good signal of like something's fishy with this account or with this purchase. So, okay, so we have this short, this is 6 different features. This is kind of like a scoped down, simplified set of features for a very first model that we might want to build. And so now we just got to build these features, right? Should be pretty simple. We just plug into the data source. We build a simple transformation pipeline, and that goes to our ML model, right? Well, we have these ideas for these features, but there tends to be a lot of implementation constraints, a lot of like practical realities about this data, where it is, how fast it is, that affects how we actually have to build this feature pipeline. And remember, the feature data has to be delivered. We got to build a model with this stuff. So it has to be available in their development space, and it has to be delivered online for us to make these predictions really quickly to approve or deny this transaction. So there's a variety of these constraints that come up, right? How fresh is this data that we have available to us? How complete is the data? Where is the data stored? How can we access it? Who can access it? And the transformation that we want to do, how compute heavy is this transformation? Do we have a lot of historical data? If it's something we don't have a lot of historical data, maybe we can't train a model with it. So it's not very useful as a feature. And when does the data become available? Is the prediction made in real time? If it's not, maybe we don't need to do certain things in the online domain. And also, for a lot of use cases, you're making a lot of predictions at the same time, so it's much more efficient to do certain things in batch. So this is just like a handful of examples of realistic constraints that someone needs to think about when they're translating the idea of the feature into an actual implementation of the feature, into actually the end architecture that they that they build to instantiate this feature in production. And this significantly complicates things, right? Every one of these questions can have an impact on what the end implementation is. And so we've kind of gone from this point of pretty intuitive ideas of what a feature could be to potentially a gigantic space of different implementations for feature pipelines. And so let's just look at like some examples. So, and yeah, just to recap. So an ML engineer's task is to, given these constraints, still extract as much predictive value as possible out of their data. And so let's look at some examples here. So for example, the feature user has previously been flagged for fraudulent activity. This one is probably the simplest one, right? How we do it, we have some historical user activity in a database. We're going to run a query against that database, or maybe this is a data lake and we're running some compute job against that. We look through all the historical data. And then we create a list of yes, no for every user. And then we have to store that offline to power our model training, because we're looking at historical model training. We need all the historical examples. And we also put that online to to be to be ready for serving to a model when it's making a prediction for a given user in real time. And so we might implement this with getting this data on from S3. This could be a Spark job that we're running against it. We might store it in S3 and load this up into Redis to do this real-time serving. Okay, so this is one pipeline that we built. Now let's kind of move to a different idea, to a different feature that we have in mind, and we'll consider how to build that one too. So another feature that we talked about, how is this transaction abnormally large, right? And so how do we do this one, right? Well, we need two types of data here. We need what is the normal transaction size data. So that comes from all of our history, our logs. But we also need the current transactions data, the current transaction size, right? And so that comes from the web application where someone's, the website where someone's making that transaction right now. So that we might model that something like this at the implementation layer, right? Having a variety of storage layers that hold the kind of like, what is the historical normal transaction size? And then there's a transformation that compares historical normal transaction size to this transaction size that comes in from the website in real time. And this is something we can't pre-compute because it comes in real time from the website, because the user just created their shopping cart now. And then processing that, say, in Python or however we want to compute it, and then passing that off to the model to make the prediction. So the point here is that this is a different architecture that you have to think about. It's another thing to maintain. Let's look at one more example. And this might be implemented on some similar infrastructure. There's a new layer here of online transformations. Probably implement that on some type of productionized Python. And so, okay, here's another interesting one. Has an abnormally large number of similar transactions been observed across the website in the past few minutes? So here we're looking at a lot of transactions, and we're looking at recent data. What has happened in the past few minutes? So this one's very different as well. This one likely involves, you're probably going to use some type of streaming data, right? You're going to look at like a stream of transactions. You're going to aggregate across these transactions and constantly be processing what is like how many weird transactions have we seen recently, and make that available for the real-time serving layer. And offline for training, you don't necessarily need to do that all in streaming. So you may do this similarly with a kind of batch compute system. And so this involves running Spark, running streaming processing jobs. This is a lot messier to build as well. And so, we're not building just one of these features. What we're doing is, our model, we had 6 features. Just for 3 features, we kind of got 3 different architectures. It's gotten like pretty crazy. And so how do we do this, right? Like if you're a data scientist, if you're just a small resource-strapped engineering team, this is really tough to do, right? It's both hard to build all of these pipelines, but it's harder and it's quite expensive to maintain all of these pipelines in production. And this is really tough. And so, this also gets to the core challenge that a lot of teams have, where ideally once you get a system up and running, it's pretty easy to keep iterating on it. But what we find with a lot of machine learning projects is for each new iteration, it doesn't necessarily result in the same architecture being applied again and again, but it introduces a new engineering challenge in each iteration, and that slows down the iteration and innovation cycle with machine learning, with production machine learning projects. And so, these small changes in the idea space, in the kind of how we want to define these features, leads to these really big changes in implementation, and that affects how costly how costly the ML project is, right? It affects how costly each of these features is. So there's got to be a better way to do this, and it really a really nice thing would be if we could decouple the kind of idea space, the defining the features, from all of the engineering challenges from implementing these features. So at Tecton, we've been working on solving this problem. We build a feature platform. So Tecton plugs into the business's data sources, the cloud data platform, and it serves the feature data both to the model for inference and for training. And it's all about making it as easy as possible for data scientists to get as much data, or rather as much value, as predictive value as possible out of the data sources they have, given the constraints that they have, which is a different framing of the problem we just discussed, right? It's our goal is to make it very easy for teams to build and to maintain in production a variety of these feature pipelines so they can maintain very accurate models. So how do we do this, right? Well, Tecton creates these production-ready feature pipeline implementations from very simple definitions that are just written in Python files. So this is basically, you have a repository of Python files. This is a super simple implementation, or a super simple definition. It's just a SQL query. And Tecton takes this Python file and compiles that to an implementation on your infrastructure. So this is the kind of instantiated feature pipeline. This is something that might have had to be figured out by the data engineer, the ML engineer before, but this is the type of thing that happens, that Tecton takes care of, and it happens automatically behind the scenes. And so, Tecton will plug into the various different pieces of infrastructure and coordinate and orchestrate amongst those automatically. So that saves time. So then you just have to think about the idea space. What is the feature that I want to build? And leave the implementation out of your core iteration loop, allowing you to speed up as you're building your ML system. And the idea, because different systems require different features, require different implementations, it's really important that such a platform is able to support a large variety of common and powerful feature pipeline patterns. And so that's what we've done with Tecton, right? We've talked about a lot of these, but there's a couple more that are very important. So, running a simple SQL query against your data warehouse, super simple, but storing it online and offline. Handling real-time transformations using productionized Python. Managing streaming operations for you. So, and all of the streaming jobs related to that, and maintaining that in production. And then also, just querying external microservices or other operational databases. These are all patterns that we see again and again across different teams putting ML into production. And it's pretty important for us to be able to support all of these implementations behind the scenes while giving a very simple and natural feature API for the users to define these features and all in one unified way. And so, when we define these features all together, then we're able to, they may compile to different implementations behind the scenes, but what Tecton's able to do is deploy those together as a single unified artifact for a production application. And so we take the repository of the different Python files that configure different features and deploy them all together, likely with different implementations behind the scenes, to provide a single real-time API for your model to get all of the fresh features from, or through the Python SDK to be able to retrieve historical training data sets. So the idea here is to make it really natural for the data scientist, the engineer, to just think about what are the features that I want to build, and not have to worry about the challenge of designing the feature pipelines or maintaining them in production. And so this gets at this idea of decoupling the definitions from the implementations, and that makes the operational ML a lot easier to build and maintain. And these feature platforms, they were able to implement and manage these features both now with the best modern data infrastructure, but also we're able to inject the best practice architectures for modern ML. So by adopting something like this, not only does it make it easier to build and maintain these systems, but you're getting a more efficient implementation and a more reliable implementation behind the scenes. So it's a value that a lot of our customers have gotten that's been quite interesting for them. Okay, so I'm just about at time. I hope this is a good recap of like some of the types of feature pipelines that we see in production, some of the challenges that people run into when they're facing these kind of like realistic constraints of the variety of data that they have, and a glimpse at a better way to do it. So thank you.
Awesome.
And also I'm available. I'm also on Slack, so hit me up on Slack if you want to chat a little bit more.
Yes. And as I mentioned before, everybody is going to be answering questions from their talks on Slack. So if you're not on there, jump on it and ask your questions there. Also, I've been seeing some stuff come through Slack, and I'm already ready to give away some swag. So I saw that
we're giving away some Tecton swag.
Yeah.
Okay.
Yeah, we're definitely giving away Tecton swag. We're giving away. So I actually have a preview of the swag that we're going to be giving away. I think I got this. If anyone can see, it's a Yeti cup that keeps your tea nice and warm. And so sweet stuff, Mike. I appreciate that.
Thank you. I was right on time, so I'm proud of myself.
Yeah, you were
okay.
perfect.
I'll sign off.
See you, man.
Thank you.
So yeah, I just saw Gary Moore is working with ML ops in the encrypted space, and I like that. You're fighting the good fight. So you get some swag. Reach out to me, Gary. That's awesome. I also saw there is someone from South Africa in here. I couldn't catch their name anymore because I was scrolling and looking for them. But whoever is in South Africa, you get some swag, and everybody's going to now say that they're in South Africa. So yeah, reach out to me and I'll put you in touch with somebody to get, there we go. More people coming from South Africa. Anyway, we got more of this happening. Another easy, great way to win some swag is to participate in this cool little photo booth session that we're having. And the photo booth session, we're going to throw the link to the photo booth in Slack and in the chat everywhere. What you do is you just go and you take a selfie of yourself. Yeah. And you make a face that, let's see if I can explain this correctly. All right. So go and take a selfie at the photo booth app, which we're putting the link in the channel right now. And then once you get the chance to take this selfie, don't just take any selfie where you're sitting there and like, whatever. I want you to think of the face you make right before you're about to push your model into production. And if that yet is still not a reality for you, just play along and live in fantasy land. So the face you make right before you push the model to production is what I want to see. And bonus points if you can throw in a pet or if you have a costume that you want to be wearing while you take that selfie. The cool thing is you click through and you'll be able to see everyone who has also taken selfies in this photo booth. It's pretty fun. So we're going to try and get that going. Easy way to win swag. I'm going to be picking out some of the funniest and best photos from there. Next up, we've got Erica and Siyun, who I have a very special connection with because I have already interviewed them in the MLOps community podcast. And I heard all about what they're going to be talking about. I'm so excited to actually see the talk now. Since the interview, I've just been like waiting and frothing at the mouth to see what you all talk about. So it's great to have you, Erica and Siyun. Good to see you all again. Welcome to the Apply conference.
Yeah, thanks. Good to be here.
So I will let you all take over And just so, yeah, I mean, I think everybody can read, but they're going to be talking about model calibration in the Etsy ads marketplace. That's it. It's all yours. The floor is yours, Erica and Siyun.
Okay, well, thank you. It's great to virtually be here with all of you. So Sayun and I are going to be talking about a topic that we have thought deeply about and worked on for the last year, which is calibrating machine learning models. And we're going to be telling you about our journey calibrating all of the models in the system for Etsy ads. So that's a talk, but widely applicable to any sort of ML system. I imagine most of you know what Etsy is, but just to give a little overview of the company, it's a marketplace, a global marketplace for unique and creative goods. It was founded in 2005, went public in 2015, and is headquartered in Brooklyn, but has offices all around the world. They sell over 100 million unique items on the site, and some areas that the company uses machine learning in is product search, user recommendations, and on-site advertising. So I pulled a listing just to give you a sense of the sort of fun, wonky things that you can buy on Etsy in celebration of Valentine's Day, which is coming up on Monday. If you want a very cute melting heart mirror for the low price of $14.99, this is the kind of stuff you can buy on Etsy, along with 99 million other things. So the system that Sayun and I have worked on is the ad product, the on-site advertising product. It's called Etsy Ads, and it's a product or a service that sellers can choose to sign up for. The way it works is that if they choose to sign up, they set a daily budget, an amount of money that they want to put towards advertising every day. And when a buyer comes to the site and searches for something such as heart mirror, the ad system will return an ordered list of items, of listings that ideally are relevant to the buyer and relevant to that particular query. And then if a buyer then clicks on one of these listings, the seller whose listing that is gets charged a small fee and for the promoted click, essentially. And we're going to go, Sayun will go into this more in the following slides, but that fee that is charged is dependent on a lot of things. It's actually calculated at request time, and it's set via a second price auction that we run in the background.
Great. Yeah, so to understand the importance of calibration within the Etsy Ads marketplace, we'll first take you through how we rank listings in Etsy Ads. So for every ad request, we score each listing and return the listings with the top scores. Our scoring function is roughly formulated as the score is equal to the predicted click-through rate multiplied by the bid. And the predicted click-through rate is the estimated probability that a buyer will click on the listing, and the bid is the estimated price that a seller will be willing to pay for that click. And both of these components of the scoring function are backed by machine learning models. So in a traditional search system within a marketplace, there's usually one stakeholder, which is the buyer. But in an ad marketplace, it's slightly more complex because there is a new stakeholder who is introduced, which is the seller. So if we take a closer look at the scoring function, we can see that we're actually trying to balance the objectives of both the seller and the buyer. So the predicted click-through rate is actually the objective of the buyer, because it's analogous to the willingness of the buyer to engage with that listing, and it is directly related to the buyer experience. On the other hand, the bid is directly related to the costs, return on ad spend, and the exposure within the Etsy Ads marketplace. So the bid is the seller objective. So within the scoring function, if we place a higher importance on the predicted click-through rate, we are improving buyer experience at the expense of the seller exposure. And if we place a larger importance on the bid in the scoring function, we are improving seller exposure at the expense of buyer experience. So now, if a seller's ad is clicked, the sellers have to pay a minimum amount required to keep their position in the ranked list. So what does that mean? So if we take a look at this example over here with the wedding dress query, we can see that two listings are ranked. So the first listing, which is this white wedding dress listing, can be seen to have a predicted click-through rate of 0.5 and submits a bid of 60 cents. And since the score is calculated as the predicted click-through rate multiplied by the bid, it obtains a score of 30. And the orange wedding dress listing has a predicted click-through rate of 0.3 and submits a bid of 80 cents, so its score is 24. So you can see that the white wedding dress listing is ranked higher than the orange wedding dress listing because it has a higher score from the formula. And we can also see that if a buyer clicks on the white wedding dress listing, it's actually charged only a cost of 48 cents rather than the full bid of 60 cents. That's because the white wedding dress listing only needed to bid 48 cents in order to outrank the orange wedding dress listing. And this type of cost calculation is known as a generalized second price auction. So that goes to say that if the second best listing or the orange wedding dress listing had a different score, the white wedding dress would have to pay a different cost. So if we take, for instance, the orange wedding dress had a higher predicted click-through rate of 0.35 compared to the original 0.3, then its score would increase to 28 from 24. And as a direct result, the white wedding dress would have to pay a cost of 56 cents rather than the 48 cents in order to keep its position in the list. So from the previous example, you can see that the predicted click-through rate and the bid have a large importance in ad ranking and the cost charged to sellers. As a matter of fact, the variance of these model scores impacts the relative importance between the click-through rate and the bid components in the scoring function. So take, for example, if we look at these distribution graphs, if our bid was constant and our machine learning models were just submitting one bid and there was zero variance to the bid, our score would be dominated by the click-through rate component. On the other hand, if the click-through rate model only outputs one single number and there's zero variance, you can see that the score would be dominated by the bid. With these two different examples, you can see that a larger variance within these distributions of scores affect the scoring function, and it places more importance on the distribution with a larger variance. So if you see this final graph here, if there is variance between the click-through rate and the bid distribution, the score is just a product of the two, and the distribution with a higher variance will have more importance within the scoring function. So now what affects these model distributions? It can be affected by a variety of many different factors. One important factor is a sampling of training data. Take, for instance, our predicted click-through rate model, where we are trying to predict an event that rarely occurs. Take, for example, within the Etsy ad system, the click-through rate might be 1%. In those cases, a machine learning model can kind of cheat the system by predicting the negative instance or non-click 100% of the time to achieve a 99% accuracy rate. So in order for us to help the model distinguish between what a positive example is and a negative example is, there are a variety of sampling techniques where we could either downsample the negative instances or upsample the positive instances so that the model learns a relationship and knows what features lead to a positive instance or a negative instance. However, although that improves the distinguishing capabilities of the models, since we're changing the underlying makeup of the training data, it also influences the output distribution of these models. Other factors that affect the distribution of model scores is the model architecture. If we change the algorithm of the machine learning model from, let's say, logistic regression, to boosted trees, to neural networks, the output model distribution is significantly changed because of how the loss function is constructed within each of these algorithms. Other techniques such as weight decay and batch normalization has been shown to also affect the output model distribution. And finally, the model complexity or the size of the model also affects the model distributions. If you look at the graph to the right, you can see two real predictions of two of our predicted click-through rate models within our system, where we were trying to migrate away from a gradient boosted trees model, which is shown in the graph in the blue, to a deep neural network model, which is the graph in the orange. And as you saw from our examples before, changing the distribution will change the variance of these distributions and also affect the weighting of these components within the scoring function. Now, the instability in these model distributions, every time we iterate it on a model, significantly slow down model development. And that's because, as we said before, the cost charged to sellers and the quality of the ads shown to buyers are heavily dependent on the output distributions of these models. In order to stabilize these costs and the buyer experience, we start to introduce manually tuned parameters into our scoring functions to kind of fit the distributions to something that would stabilize these factors. So previously we mentioned that there was a scoring function, which was simplified from predicted click-through rate multiplied by the bid. However, with this new system, the real score was actually a function of the predicted click-through rate, bid, and a set of 3 constants, alpha, t, and b. The alpha constant was an exponential constant, which was placed onto the predicted click-through rate to weigh the components of the predicted click-through rate and bid differently. So as we increase the alpha constant, we would weigh the click-through rate more in the system, and as we decrease it, it would weigh less. The t and the b constants were placed actually on the bid component to manually fit the distribution to a distribution where it would stabilize the cost. So with the introduction of these different parameters, it became difficult to decouple the impact of the model improvement from the impact of tuning these constants and the scoring function. So, and as a result of these constants, we had to spend extra time in the experiment cycle to tune the scoring function and the constants. So a typical experiment cycle looked like this. We would first iterate on a model until we would find offline improvement gains. Then using these new models, we would simulate an offline auction to determine if there are shifts in costs charged to sellers and the buyer experience. If we did notice a significant shift to costs and quality of the ads returned, we would then tune the parameters and the scoring function in an offline manner until we came to a set of constants that we were happy with experimenting online. And then with those parameters, we had to tune those parameters once again online because the offline results are not directly related to the online business metrics. So after fine tuning those scoring function and the parameters, we would then launch the experiment and rerun this entire experiment cycle. So one thing was that the scoring function tuning steps took maybe from days to weeks to even months at certain times, and took valuable developer time into this, something that didn't bring too much value or any learnings into our system. So ideally, we could cut off these 2 steps from our experiment cycle and leave it to just model iteration, offline auction simulation, and experiment launch. So what we needed to do was that we needed to stabilize our model output distribution so that we don't have to manually fit these distributions to something that would stabilize costs and the quality of ads. And the answer to that problem was calibration. So calibration is a machine learning technique that's used to fit the output distribution of a model to an empirical distribution seen in the system. And one nice property of calibration is that it preserves the order of the original scores. So it doesn't affect the main metrics or offline metrics such as AUC or NDCG of your models. So if we look at the graphs below, on the left-hand side, it's an actual graph of the predicted click-through rate model that we had, where it output a distribution that looks like a bell curve. But in actuality, within our system, the distribution looked more like a power law or log normal graph seen in the empirical distribution side. And in order to kind of transform that prediction distribution to something that resembles the empirical distribution, we just calibrate that model. So why this works is because the empirical distribution and the buyer behavior is pretty stable day to day, where you won't see like 1% click-through rate in one day and then like 10% click-through rate the other day. Since the empirical distribution is extremely stable day to day, we can calibrate our models to output a distribution similar to the empirical distribution, and then that output distribution wouldn't change that all too often. So if we make modeling improvements on the underlying model or change like the model algorithm from logistic regression to deep neural networks, we could force all of these models to output the same distribution. And added benefit of calibration is that the model predictions now become interpretable as probabilities. So the guarantees of interpreting the predictions as probabilities and the stability of these probabilities unlock added benefits, which we'll go into later, where we can start to use them in downstream systems. So we wanted a lightweight method to validate calibration was right for our marketplace and to ensure that it wouldn't affect like the entire system in a drastic manner. So we decided to use Plaid scaling as a lightweight method to validate this. So Plaid scaling is a parametric version of the sigmoid function, and it transforms raw outputs of a model and uses that features to an additional logistic regression layer. That logistic regression layer learns 2 additional parameters that transform the raw outputs before transforming the outputs into probability space. One thing to know about calibration is that we want to keep the learnings from the original model. So when we train the calibration layer, we want to freeze the original weights of the model. So take, for instance, this sigmoid function on the right-hand side. It's the regular sigmoid function that allows us to transform raw outputs of a model ranging from -infinity to infinity to a prediction ranging from 0 to 1. Now for Plaid scaling, you can see it's a minor variant of the sigmoid function where we introduce the constants A and B. So the A constant affects the width of the distribution. And as you can see, if we increase the magnitude of the A parameter, we tighten the distribution. And if we decrease the magnitude of the A parameter, we widen the distribution and increase the variance. On the other hand, the B parameter essentially translates the distribution left and right. Now, we found out that calibrating the models with Plaid scaling was extremely easy. On the left-hand side of this diagram, you can see our old workflow where we would train a fully connected deep neural network using some downsample training data and then attach a sigmoid layer to transform the raw outputs to a prediction space. In order to calibrate this model, we basically took the old model, just froze the weights, attached a Plaid scaling layer on top of our previous deep neural network before the sigmoid activation layer. And then in order to train that Plaid scaling layer, we just used a holdout set of calibration data. And to show you how easy it is, here's a screenshot of the implementation in TensorFlow. But you can see the constants A and B are trained, and it just modifies the raw outputs of that model. Now with calibration, it required a little minor adjustment to the ETL workflow and the model training workflow because we needed a separate holdout set that contains the empirical distribution in order to calibrate this layer. So in this diagram, you can see this was our old training workflow where we would train an uncalibrated model by using the downsample training data, which has a distribution uncharacteristic of the actual system. And then we would evaluate that model using the empirical data set. Since the model was trained using that downsample data set, its predictions would resemble a distribution close to the training data. Now, in order to calibrate this model, we had to partition the evaluation data set because the evaluation data set is the one that contains the empirical distribution. When we train the model, we train it regularly using the downsample data set so it can distinguish between positive and negative examples. But then when we calibrate the model, we use the empirical distribution within the calibration data set. And as a result, the calibration model will now output predictions that resemble closer to the empirical distribution. Now, the question is, how can we assess or how can we evaluate how well calibrated a model is? And a simple way to assess how well calibrated the model is by computing the calibration ratio. So the calibration ratio compares the average of the predictions against the actual rate observed in the system. So a ratio of greater than 1 indicates that your model is overconfident and it's outputting predictions that are greater than what is seen in the system. And a ratio less than 1 means that your model is underconfident and it's outputting values that are less than what is seen in the system. Now, although this metric is great for a general overview of the model, you might want to know in which prediction ranges the model is performing better or worse in terms of calibration. So we could actually compute the calibration ratios across more granular prediction intervals. So in order to do this, we would bin our predictions across specified intervals. In our example here, we're separating it out into 4 different bins, equally spaced 0.25 apart. In our first example here, we have 4 negative instances where there were no clicks, and these are the outputs of our machine learning model. If we average the predictions and the labels, we get an average prediction of 0.1 and an average label of 0 within this interval. If we do this in the next bin, you can see that there's 1 positive instance and 2 negative instances. And if we average the prediction and labels, this is the result we get. And furthermore, if we just complete this exercise across the next 2 bins, you can see these are the average predictions and labels across these 2 bins. Now, you can imagine we might want to form more granular intervals. Rather than 0.25, maybe we want to make 100 bins and space them out 0.01 apart. In that case, looking at these average predictions and labels might be hard to distinguish where your model is under or overperforming. So we can construct what is known as a reliability diagram. So basically, the reliability diagram plots out the predicted probability against the observed probability across all prediction intervals. Now, if we take, for example, some of these points we saw before in each interval bin, we can plot these points out within this reliability diagram. Now, as you may know, you can see that there's a blue line, which is the identity function across the reliability diagram. And if a point lies on that identity function, it means that the model is perfectly calibrated within that prediction interval. And if a point appears lower than the identity function, it means that our model is overconfident within that prediction interval. And if a point appears above that line, it means our model is underconfident within that prediction interval. So the reliability diagram is a great way to visualize which areas of predictions that your model may be less calibrated in. And we can see an example in the next slide right here, or the next slide after this, but after calibrating our models, we are able to observe that our models were being calibrated properly. So here's a dashboard showing the calibration ratio metric for our uncalibrated and calibrated models. The yellow dot represents the calibration ratio for our uncalibrated models, and you can see it had a calibration ratio of roughly 33, which means that our predictions were roughly 33 times more than what was observed in the system. So if our system click-through rate was 1%, our model was outputting predictions of 33%. So after calibrating the model with Platt scaling, you can see we achieved a close to an ideal ratio of 1, as you can see in the green dot over there. Now we wanted more granular assessments of calibration within our models, so we generated the reliability diagrams for our models. On the left-hand side, you can see an uncalibrated model where our models were overconfident in predictions across all intervals. But once we calibrated our models, you can see that the dots lie closer to the identity function, where most of the predictions within all intervals were very well calibrated, except for the intervals where we had less data. And if you look at the graph, the prediction ranges where it ranges above like 0.5 or in higher prediction ranges, we have less data because there are less and less listings within that range that have such a high click-through rate. So we don't have enough data within those ranges to calibrate those ranges properly. So now we had to perform a final tuning experiment with these new calibrated predictions because the calibrated predictions significantly changed the output distributions, and the constants were finely tuned to our previous system. And launching the calibrated models as is will cause major disruptions to the seller costs and the buyer experience. But one great thing about calibration was that we were able to simplify the scoring function by removing most of these manually tuned parameters because now the predictions became stable. So while the old score was this function that you see here, the new score became a simple predict click-through rate to an exponent multiplied by a bid. And that exponent is still there because we want to have the lever to prioritize the buyer or seller experience. Now with the stability and the interpretability of these predictions, we were able to apply the calibrated predictions to more product applications. One use case was filtering low quality ads in our system, since filtering low quality ads can improve buyer experience and help long-term marketplace health. Since these are stable, we can introduce thresholds to filter out these low quality listings. And if you look at the query to the right for a wedding dress, you can see that these wedding dress hangers have low predicted click-through rate. And if we place a threshold of 0.06, we will be able to filter out these wedding dress hangers and put out a result set of only wedding dresses. Another use case is that we can flexibly change the page layout based on the quality of ads at a certain period of time. And if we see some type of day where we have ads of low quality, we can push down the ads and show more non-ads on the top of the page. And if we sense that we have higher quality ads at request time, we could show them at the top of the page. And finally, if we have a comparable metric between the non-ads and the ads, we can actually blend the results and show it in a non-fixed order. And thank you for listening to our talk. This project was a year-long project from inception to completion. Couldn't have been done without my manager, Erica, and my entire team. And it was a very fun project. And as a reminder, please calibrate your models, and we'll take questions if you have any time.
Yeah, I want to jump in and ask a few questions that I'm seeing coming through Slack, which are pretty awesome. And that was a great talk. It did not disappoint. So congratulations. Thank you so much for that. The first question that I wanted to ask was, the estimated PCTR seems conditional on the query string. For example, wedding dress versus dresses for weddings. Presumably, the first refers to just white wedding dress, but the later could include bridesmaid dresses. Was the query string used as a feature in any models?
Yes, the query string was definitely an important feature for both the predicted click-through rate and the model that affects the bids. That is the short answer.
Yeah, I'd add on to that too. I'm not sure if this is what the person asking the question was getting at, but the calibration step, we calibrate all our models globally. So everything is calibrated to the average predicted click-through rate, but it is true that different segments, you can segment the traffic by different ways, and we'll have different average click-through rates. And so a follow-up set of work that we want to explore is to calibrate conditioned on various different segments. You can imagine calibrating by platform or calibrating by country. You could try to calibrate conditioned on query, although it's a long tail of many different queries. So I'm not sure if that's what they were getting at, but yeah, certainly query is a very important feature in both the bidding system and the predicted click-through rate model, but it's currently not an input to the calibration step.
And so there's another one in here, and Erica, I see that you answered in Slack, but I think we should just ask it again because people who are not on Slack may want to know this one. From Julian, do you have any processes to deal with pricing inquiries from the seller? Said differently, do you ever have to explain how the fee placed on the seller was figured out?
Yeah, that was a great question. So I put this link in Slack a few times. We did write a blog post about it. Maybe the short answer is that sellers do have a dashboard available to them. We give them a bunch of data and information about their campaign. We tell them which queries they're ranking for, what listings are ranking for those queries, and the cost, the fee that's associated with that. Unfortunately, with many of these complex ML systems, it's not so easy to exactly explain what's going on, even for us. So we didn't get into this, but it's a multi-step ranking process that determines both the bid price and the predicted click-through rate. And there's a second price auction running, and the entire thing is run on, many neural networks, lots of features and data. So it's not so easy, but I think it's something that the company should strive to get better at, because I think people do deserve to know, how their money is being spent. But it is a kind of classic explainability conundrum with these ML systems.
Incredible. Thank you both for this. I just cannot thank you enough, because when you came on the MLOps community podcast, like someone just said in the chat here, like, you literally opened my mind. I had not thought about this. And then, funny enough, as life works, I went to a few other meetings that same week, and people were talking about similar problems that they were having. And I said, oh, you may want to check out this talk we just had with Erica and Siyun, because the calibration thing might be what you need. So it's perfect. Hopefully it helped a lot of other people.
10 lines of TensorFlow code and a lot of offline experiments. Yeah.
Yeah. And what you didn't mention was the 4-month bug.
Oh yeah, well, right. Once they fixed their bug that took 4 months, it was 10 lines of TensorFlow code.
Yeah, and shout out to also you for the awesome war stories that you presented in that podcast that we had. So everyone, if you want more of Erica and Siyun, go check out their podcast with me on the MLOps community, Spotify or Apple, whatever you watch. So
Maybe not.
We're going to keep cruising. Yeah.
It was great to be here.
Thank you all. We'll see you later. And I'm going to let you see what kind of swag we're giving. So I think, let me share my screen real fast and you get to see what we're going to be giving out, because I've been talking lots about the swag and I've been seeing there are some really cool and funny pictures coming through the the gallery, which is awesome. We'll give away some swag for those people. Remember earlier I mentioned we had some partners and sponsors. I should probably thank them and let you know who they are. This is a great one right there, but they're all pretty awesome. And there are some free things that you're getting here. So you get a free 30-day subscription to O'Reilly and the Sequence. If you did not get that, just let us know in an email or in Slack how you can get a hold of that, and we'll hook you up. I mentioned this before, but here it is. Here's what you're winning. Oh, so exciting. I told you there was a picnic blanket. Look, that Databricks thing is a picnic blanket. We've got some Mirai totes bags. We've got Data is my rock, Tecton shirt and mug that I mentioned, ternary data, stickers and Run AI, I think socks, Great Expectation socks, you name it. So let's give it away. This is my favorite part. Whoever has the frog that they hold when they deploy a model, you get some swag. Whoever that is, you're getting some swag. I love the dogs. I love the cats. That's great. But that's all for now. Keep them coming. I'll probably choose another few of these because they're amazing. I also wanted to give some swag out to Julian. And here we go with the last name, Carrasquillo. Julian, you've been asking some awesome questions in Slack. So get a hold of me and I will put you in touch with the right people to get swag from. Next up, we've got another incredible speaker. All right. And before we jump into the next speaker, I want to also mention that we're having a poll. And the poll is usually when we have all kinds of funny questions that we ask people. So we ask you to go and fill out the poll. It's like simple stuff. What do you consider yourself? How are you an MLE? Or are you a data scientist? That kind of stuff. How has it been? How has your process been for putting models into production? And what I'm really excited about, what really I want to hear, and we tend to give out good swag on this one, is the models gone rogue story. You just heard me talking with Erica and Siyun about their war stories. I want to hear some of your war stories because we will talk about them later if they're any good. And that's all for now. There's going to be another break after this speaker, and I'll probably be giving away more swag. And I promise you, I'm not going to just talk about swag the whole time that I jump on screen, because I realize I have been doing that a little too much lately. Now, let's hear it from Dhruba Orthakur. All right. He is the CTO and co-founder of Rockset, who you just saw some t-shirts from. The Data is my rock was one of them. And Dhruba, how you doing, man? I see you are here with us.
Yeah, thank you. Thanks a lot. I was attending your previous talk and it was great fun.
Nice. Very cool. Right on. Well, I'm going to hand it over to you and I look forward to hearing what you have to say.
Sure. Yeah. Hey, thank you. Thanks a lot. Let me present my slides before I go there. Okay. Cool. Hey, thank you. Thanks a lot again, Dimitro, for introducing me. I really appreciate it. I know a lot of folks here are very much machine learning focused. I'm really excited to hear some of their stories as well. And as you folks, as practitioners of machine learning models on operations, you probably have all experienced like kind of a data analytical backends, right? Because you first need to, or at some point in time, you would have to deploy your kind of models in production. And that's the time when data analytics becomes super relevant and useful. So today I'm here to talk a little bit about the data analytics side of the story. How can you run these machine learn models in production on large data sets when data is changing rapidly and you want to deploy more models and you want to make sure that you are operating on the latest data. So a quick introduction about myself. I am the CTO and co-founder at Rockset. So Rockset is a data analytics engine that focuses on real-time analytics and serving real-time machine learning models in production. Prior to Rockset, I was the founding engineer of an open source database called RocksDB. Some of you might have heard about it because it's a very high performant key value store that is used to run some of these big machine learning models in production at Facebook. That's when I was building RocksDB. This was probably like 8 years back. Before that, I was building a lot of Hadoop file system. It's again, the granddaddy of all kind of big data and machine learning that ever started. This is back in 2006, I think, when I was doing a lot of Hadoop file system. I was the third engineer in the project. And at that time, I didn't realize how big Hadoop is and how it's going to revolutionize the whole kind of the data industry in general. I've worked on some other projects over time as well. So today, the talk that I'm having here is mostly about talking about how can you serve these big machine learning models that you have built in production systems. So I'll talk a little bit about the evolution of how we have got data processing in general, how data processing has evolved from batch to real time. And I'm going to focus a lot on what, as a data practitioner, what are the things that I'm going to look for to see what kind of backend systems I should use for serving these big models in production. Again, I'm going to take questions, so please ask me questions. Please put it in the Slack. I might pause a minute or two in the middle just to kind of answer your questions and answer them as we go. So where has data processing been? Again, Hadoop is where a lot of big data processing started way back in 2006 or 5 or somewhere around there. The systems were very much batch processing at the time, where you collect a lot of data, then you build your models for maybe a couple of days and then serve it in production after a few days or a few hours. You don't deploy models like every day or every week. That was kind of where most of the big data processing systems started. Over time, we see a lot of Spark, of course, right? This is, again, another critical piece of our infrastructure where maybe there's a lot of ETL processes to be done because you need fresh data to run your machine learning models. And so the latency of these models, the latency of fresh data that they get is maybe a few minutes or a few hours at the most. And over time, people are moving to more real-time processing, which means that can I deploy my models in real time in a few millisecond latency or a few second latency of the real data that's coming into my production systems. About real-time analytics, I'll give 2 or 3 examples of how I have seen from very close, because some of our users do this, is that how to build models and how they deploy it in production, especially when they're very much focused on real-time analytics. So this is a great example. Like take, for example, there is a company which is maybe tens of thousands of trucks on the road. They're like shipping goods from one place to another. They're like delivering construction material from one place to another. And they're really sensitive about how the fleet is being managed. The vehicles might get stranded sometimes. They have sensors in these vehicles, and they want to make sure that if there is certain signals coming from these sensors, their machine learning model in the backend can actually process them in real time and immediately figure out what is the reaction or what is the decision to be taken to fix the issues that are coming into their delivery system. This gives them a lot of bang for the buck because their operations become really simplified and smooth because decisions are made on the most real data sets that they're getting. Another use case that I'm seeing very close are about online gaming systems. So hundreds of players or thousands of players are playing an online game. And there's a machine learning model that kind of matches players with the games that they play, or as soon as a player logs in, the system needs to match him with a game event that is being played with a similar skill levels of users. Again, the model has been built, but then how do you run it in production where it can look at data that has just come in a few seconds back, like who is playing the game right now, who are the people who are logging in, and then do this matchmaking in real time. Another great example of where real time is super useful for some of these models that are being used in production. So real time is the focus of this talk today. Real time essentially are difficult systems to build. Real time systems are usually hard. So a lot of machine learning models in general might be deployed maybe a longer periodicity on data that is kind of stale. But here we are talking about how can we build systems, or how can we decide which systems to use when we need our models to be running on real-time data. If data is changing rapidly, what are the things I should look for to figure out what systems to use to deploy my models in production? There are a lot of data systems out there. Of course, you might be familiar with some of them. All of them claim that they're all real-time. You can run models on large data sets in production, and those models can look at the most recent data. So it's kind of sometimes difficult to separate the wheat from the chaff and like figuring out which ones would actually be useful if I need real-time analytics. So the talk again here is to kind of declutter this space and talk about what are the things I should look for as a data practitioner. I should look for to decide which system to use. So I have a checklist of items, and I'm hoping that this checklist make things easy or useful for a lot of our data practitioners. These are the kind of things that I usually use myself to evaluate which data system to use for deploying my models in production. I have a list of eight characteristics that I typically use to evaluate these systems, and I'm hoping that you can use some of these points to consider, or consider these points to evaluate your data system as well and your data application as well. I'm going to cover only 3 or 4 of these today. The first one that really matters to a lot of systems that need to deploy models that need to look at real-time data is bursty traffic. So in production, there is always bursty traffic. What is bursty traffic? It's about the variations of new data coming in or the amount of queries coming into your system, right? Into the system that's serving your models. Take, for example, Amazon Prime Day. On that day, the first time it was shipped, this is a great article that they've written, how the load on their system increased like 3 times compared to a normal day. So this is bursty traffic, right? Your system has to deal with these kind of bursty traffics. When I was at Facebook, I saw that on Halloween day, the photo storage system just exploded. A lot of people are putting in photos. It's like 2 or 3 times more than a normal photo sharing day in the Facebook world. So how does the system, how did Amazon handle that bursty traffic? There are two ways that they handle bursty traffic. One was that their backend was designed for the cloud, which means that they can scale up and scale down system when it's needed and when it's not needed. And also they had a disaggregated architecture. And this is the point that I really wanted to double click today. What is the disaggregated architecture, and why is this architecture really useful for companies like Amazon and Rockset and other folks as well, to make sure that we can handle bursty traffic and serve these models even when there's a burst of data. Again, when we're talking about disaggregated architecture, the two pieces of infrastructure that are needed to solve or to serve these models are obviously data, but then to serve the data, you need compute and you need storage. So they're 2 different things, right? Compute and storage are 2 different things. So compute is how much processing you need to serve the model, and then storage is how much total data set you need to look at when you're evaluating this model and doing some inferencing. So the 2 different things, the compute is very much like, say, the brain that you have, that all of us have, which basically is used for computation. And to scale it up and down, you need to do a certain set of exercises. Maybe you need to play Sudoku puzzles, or you need to do some other kind of puzzles to keep your brain active and functional and able to perform. But on the other hand, storage, which is where your data is very much like, let's say, the body that you have, which is you need to do a different set of muscles or muscle exercises to be able to keep in shape. So just like that, very similar to this is how the disaggregated architecture works. It basically separates the compute and storage. So you can do two different things to these two pieces to scale them up and down when there is more load in the system. A very new way that has arrived in the last few years is that a lot of these systems use the aggregator leaf Taylor architecture to kind of have this data infra so that you can scale up and down compute storage separately. So in this picture, I'll spend maybe I'll double click on one or two boxes of this. So data is coming in from, let's say, your production systems, which are like databases, data streams, warehouses, data lakes. You're doing some machine learning, or you're evaluating the model as part of the model as part of the Taylor process, which is essentially doing some pre-processing, and then storing this data in the leaf nodes, which is where all your storage is. And then when queries come in from your users or from your applications, they come in through like a two-level aggregator that hits the leaves and returns you back. So the key part of this is that this architecture separates the writes and the reads. So the writes, or the new data, is happening on the left side of this picture, and the queries are all happening on the right side of this picture. So this is basically follows the CQRS pattern that many of us are familiar with in software, where the writes are completely segregated from the reads. So this is the advantage, is that even if you have bursty traffic, the bursty traffic could mean a lot of high volume data. So the tailors scale up, but it doesn't impact your queries. Your queries can still get the low latency that you need. Similarly, if your queries increase suddenly and you have a lot of aggregators, but your latency of your data or your data freshness is not compromised because the tailors can keep up and keep ingesting new data to serve your models. So this is this is not a this architecture is kind of new, but it has been first populated, I think, as far as I know, in the Facebook ALT. Facebook uses this architecture for serving the machine, for serving the feed. Like when you log into the Facebook app, you probably see all your friends post comments, likes, right? There's a very complicated machine learning model in the backend serving that data. You don't see all of your friends' posts. There's like relevance matching, sorting, ranking. A lot of things happen in real time before you actually see the feed. And this feed is generated in real time. The moment you click refresh, there's a query that goes to the backend, runs this model in production on most recent data, and then sends you results. At that time when I was working at Facebook, we saw that user engagement increases rapidly when the data latency is low and when the data is real time, right? So the focus of this ALT architecture that Facebook uses was very much to kind of make sure that data is always fresh and it is a real-time analytics backend. Similarly, LinkedIn also uses the ALT architecture for the follow feed. They have published some blogs that we can talk about. I just put it for reference here. I'm not going to deep dive there. So that was the first thing we talked about is bursty traffic. And we said that bursty traffic, we should analyze a data system based on how can they handle bursty traffic. Do they use the ALT architecture? Or do they use a very batch processing architecture? That will distinguish, that will tell us which system to use if I need real time and which system to use if I need batch. Now, the second point in my checklist is about complex queries. So your data system, the way when I evaluate a data system, I look at it to see, does it serve complex queries? And if it does, that's the real one that I need to use for my machine learning models, because usually when I'm serving these models in production, a lot of complex analysis needs to happen right within a few milliseconds before you can actually serve it to production. Very early on, I was, like I said, I was part of the original Hadoop team back at Yahoo in 2005. And one of the first use cases I still remember where Morgan Stanley, one of the financial companies, they were using Hadoop and they were actually looking at a lot of mortgage instruments, a lot of deeds, lots of financial documents that they have to figure out how to give a loan to a customer, right? And that needed a really complex query that needed to look at 5 different data sets to figure out what is the rate at which I can give a loan to a person or a company. And this was all done using Hive on Hadoop. So Hive is a very complex language. It supports SQL. We can talk about it as well. Because Hive was used at the time on top of Hadoop because it had to do aggregations, to do joins, and it has to combine these data sets to give you your credit score, for example, or a company's loan rate. The challenge with some of these backends is that not all backends can support equally complex queries. So this is a great feature for people who is picking a data system to figure out which data system to use based on, can they support aggregations? Can they support joins? So joins usually is a very complex backend operation where you have to join two tables. For example, in this case, there are two tables of, say, a size 50K and 150K records. But when you join it, the intermediate data set would be really big. So a lot of data systems don't support joins because they say that, well, you don't ever have to join two tables when you're serving models in production. But I disagree because I think it depends on the complexity of your model. Now, query optimizers obviously have to support joins as well automatically. So this is another thing that you can check to see how can the query optimizer handle this automatically for you. Sometimes it's difficult to kind of sometimes it's difficult to figure out if you're comparing two data systems to compare and figuring out which one to pick. Sometimes both the data systems might look the same. It's like if you look at two birds, if maybe you're walking down the park and you see two black birds on the tree, you might think that, oh, they're the same things. But actually what happens is that when you go closer, you probably see that it's possible that you could actually have mistaken a cuckoo for a crow. And so they talk completely different language. And this is what I mean by data systems that might look same from far away, but they're really different when you go close by and you see, do they support joins? Do they support complex queries? And the ones that support joins are really useful for analytical systems or analytics that you want to use to serve your models in production. A lot of data systems are moving to SQL in general because SQL supports complex language, complex query language. Kafka, MongoDB, all of them are moving to some flavor of SQL. And even when you look at developers, a lot of developers love SQL just because it's a very complex and powerful language, and it's a very expressive language, and it needs to support joins. So this is the second point that you can use to kind of compare and contrast different data systems when you're in the process of picking which data system should I use to serve my analytics. The third point in my checklist that you can use to figure out which system to use to serve your analytics is, does the system have flexible schema? So this is important because usually machine learning models are running on data that is semi-structured, that is data that's coming in not fully formatted. And if you want real time, then you cannot afford to do a lot of cleaning and pipelining and making it ready for your production models to run. So take, for example, there are two different records coming in. And here you would see some records have more fields than the other records, right? So you need to have a system where your system can handle these two records without having to do a lot of pipelining, flattening, or cleaning. This is what I mean by flexible schema. Does your data system support flexible schema? Because flexible schema is messy. Some of it you have to clean up, which adds delays to your system. You could do that, but it adds delays to your system, and the system is not real time. It also, if you have flexible schema, it also makes you move faster because you can deploy new models in production without having to take a downtime of this. So is flexible schema a new thing, or has it been in existence for a while? So this is the question that I sometimes get from a lot of my people whom I chat with. And it's not easy. Not everybody has jumped onto the flexible schema bandwagon because sometimes it's tough to do it, especially because you cannot get SQL queries on flexible schema. So this is the challenge for a lot of data systems where you have JSON data or semi-structured data, but then can you run SQL on it? And you cannot because you need to first clean up and and make it better or flattened before you can actually run it. So Rockset has a way to do this. I don't want to deep dive here, but you can go look at some of the Rockset blog posts on how Rockset actually can take JSON data and make SQL queries out of the end. Other systems also, they have trouble. Take, for example, Postgres. You to do an alter table, add a column, you have to take it off. You have to keep it offline. CockroachDB, very difficult. I shouldn't say very difficult, but easier than Postgres, but still there are big limitations on changing schemas online. So you have to take it down. And then Hive obviously is very flexible, but again, it's not the most performant system that you could use. So again, flexible schema is a great way for you to figure out, should I use this data system or shall I use the other data system for serving my real-time analytical needs? The fourth is about low latency queries. So a lot of these machine learning models are complex in nature. We already talked about it. But then they also need low latencies because a lot of it is user-facing applications or leaderboards for gaming systems, right? Or some backend or some other app that cannot afford to wait for 10 minutes before the query returns. So how can we get low latency queries? So this is an example of there's one technique that a lot of data systems use to give you low latency queries. That's called indexing. And what is indexing? Indexing is essentially taking all your data and then creating pointers to this data so that you can get to the data when a query comes. A simple way to explain is that, let's say you have a book of 500 pages and you're looking for a string. One option is to scan all the pages and find the page where the string exists. The other option is to go to the end of the book and look at the index that somebody's already built for you, and then use the page number from there and go back to the page where the string appears. So you can see how fast the indexing technique is compared to scanning all the pages of the book. So this is what is a database index. It builds indexes so that you can query the index, so your queries are really fast, and it takes less CPU, less compute to serve the query. So indexing is a standard technique. Like when I used to work at Facebook, Facebook has a database called a social graph. And there are inverted indexes built or secondary indexes built on this social graph so that you can answer queries like, when you do a Facebook check-in, you want to see all the people who check into the same place. Now you can use the inverted index or the secondary index to find out all the people who are checked into that location earlier. So indexing is a really powerful way to serve these complex machine learning models in production, and queries become really fast. So this is, you can ask, if you're trying to consider two different data systems, you can ask yourself, does the system support indexing? Can I use it to make my system, to make sure that my queries run very fast and maybe in a few milliseconds or a few seconds, and can still process a lot of data as part of the query. So indexing all fields is definitely something that you can consider or make your data system do when you're serving queries in production. And it's not just indexing, it's also the queries. If you make two different types of queries, the query system should be optimal or optimized enough to automatically pick the right index to use, so that as the machine learning model application developer, I don't really have to worry which index to use when I'm serving that model. So again, traditional ways, they mostly do MapReduce and scanning method, and the new systems which do real-time model serving, they mostly use a converged indexing technique to serve these models, large models in production. Any questions so far? Okay, let's go. Let's keep going. So mutability is the last and the final point that I wanted to touch upon is mutability. What is mutability? Mutability is the way that is a feature where you can actually update an existing record, right? Instead of appending to existing records. So take, for example, a Facebook event record. Somebody posted a Facebook event like a whale watching. And so now there's a lot of machine learning model that runs in Facebook, which detects if this event is a spam event, right? So how does it figure out it's a spam event? It has to look at a lot of data and then mark the item as is this a fraud event or is it a valid event? So if it's an immutable system, traditional data systems, you write all the original events into one place, and then you'll add you add the marker. Your machine learning model will add a marker saying that these events are bad, and you can write it to a different place. And then when you're querying, now your query system has to combine these two data sets, like the events itself, and then look at another place to see, is it marked as spam before the application decides whether to render this event to the end user or not. So it's a complexity for the user when you have an immutable system. On the other hand, if it is an immutable system, which basically supports updates, let's say you have these 3 records and the spam detection finds that the first one is a spam, it is just going to go update it and mark it as spam. So now the application, as an application developer, it becomes very easy because the data is mutable and the machine learning models are updating these models in production or updating fields of the data in production, and the application developer makes it really has a much easier life building applications. Again, mutable systems are making a comeback. You probably see it in real life as well, like Snowflake, Redshift. It's very difficult to deploy real-time models in production because they don't change. They're all append-only systems. Whereas MySQL, Sybase, and other, and even Oracle or even Rockset, they're like all read-write systems. So you can actually leverage the mutability of the system to deploy real-time models in production. So those are the 4 or 5 checklist items that I had in mind that I thought I will discuss with you. As a wrap-up, I just try to re-summarize what we discussed today, and I hope to get a lot of questions from you on Slack or after my presentation. So a lot of machine learning models, we talked about fleet management, we talked about gaming systems, they're all moving from batch to real time. They have to make sure that the models run in real time mode. And to make that happen, there's a lot of challenges. A lot of people have adopted the modern real-time data stack. And then this discussion was mostly focused on people who are trying to pick or select between different data stacks and how can they pick the right one. So this is a checklist that I have, which talks about the things that I should look at to figure out what data systems to use if I want real timeliness of my backend serving. And of course, Rockset is one of them, which basically is a real-time analytics system. So you can actually deploy large data sets, or you can deploy machine learning models on large data sets that are constantly changing or fluctuating or being updated without having to deal with that hands-on. The system does the right thing so that all your queries are fast, and you can actually get maybe 1 second of data latency compared to when data is produced till the time when the data is actually being used by the model to make decisions. So that's the advantage of using Rockset. And Rockset uses all these 8 checklist items or tick marks, each of the checklist items that I have here, which describes how the system works. So again, thanks a lot. I will take some questions if there are any, but you can also send me email or contact me at on the Slack channel as well.
Yeah, for sure. I have one quick question for you, and then sure. I know that time is of the essence. You were working on Hadoop in 2005, and you've been in the game since then. Can you give us a war story?
Oh yeah, absolutely. I still remember actually, I'll tell you a very interesting story there, right? The first time we ever put Hadoop on a system that was running Oracle earlier, people used to have a lot of difficulty producing reports within 24 hours. And then when you put like a maybe 30 node Hadoop cluster or maybe 20 something node Hadoop cluster, those reports used to come out in 15 minutes, right? The war story was before actually Hadoop happens, which is what we are struggling to figure out how to make these reports run faster, because if the daily report is more than 24 hours, there's no value to this report, right? And then when it took 15 minutes, people were thinking, is this magic? Is this black magic? What are you folks doing? So it was real fun at the early days.
Excellent. Well, thank you, man. And there's all kinds of questions that have been coming through in the chat. Please direct them to Slack. I know Dhruba is going over there right now to answer all of your interesting questions. And if you are not in the Slack, we're going to drop a link to it right now so you can jump into Slack. We're going to keep cruising though. Thank you, Dhruba. This was
Hey,
awesome.
thank you.
I really
Thanks a
appreciate
lot.
it.
Thanks a lot. Bye.
So a little bit of house cleaning before we jump into the next speaker. I want to remind you that we have got that poll where I really want to know about your war story, your model gone rogue story. I also want to present something to you all. I'm going to let you choose what we do in the first break. We've got a break coming up in about 30 minutes, or maybe it's in an hour. Sorry, I got to check that one. But we've got a break coming up soon-ish. And I would like to know, do you want to have me lead a meditation, or do you want me to randomly improvise on the ukulele that I brought? Which one will it be? We're going to throw a little poll in Slack, and we will ask you to vote on your favorite choice. I see somebody is saying both at the same time. A ukulele guided meditation. It could be possible, but that has never been done before. I might be breaking new ground. I'm going to just stick with one or the other. So vote in Slack. That's happening in not this one, but the next one, in the next break that we have. For now, we've got someone that I think I can call my friend. Stefan, are you around here? I'm paging Stefan to the stage. There he is. So last time we spoke, Stefan, you were threatening to open source, or the last time you were on here, I guess, and even the last time that you came onto the MLOps community podcast, you were threatening to open source Hamilton. And since then, you open sourced it. So we want to hear what is up now. What have the updates been? How's it been going? I'm excited to hear. It's been almost like a half year or maybe a year since we last heard from you about Hamilton. So I'm going to hand it over to you, man.
Cool. Thanks for having me, Dimitris. Yeah, definitely. Hopefully I'll answer those questions in this talk. So my name's Stefan Krafchik, and I lead the model lifecycle team at Stitch Fix. And I'm going to talk to you today about Hamilton, a micro framework for creating data frames, and how we use it at Stitch Fix. So what to keep in mind for the next 30 minutes or so is, one, I'm going to try to convince you that Hamilton is a new paradigm to create, data frames, but not only that. The second is that it's a productivity boost for teams. Hopefully, I'll give you enough motivation to show that. And then the third thing, it is open source, and you can look at all the code, and we do have a community on Discord. So outline. I'm going to start with the backstory. So how did Hamilton come about? Well, there was a data science team named the Forecasting Estimation Demand Team. They're a team of data scientists responsible for operational forecasts that the business makes decisions on. So for instance, what should our staffing level be at a warehouse? It's also one of the oldest teams at Stitch Fix, so their code base has been around a while. Their workflow to create forecasts looks something like the following. They get actuals, so marketing spend, signups, create a featureized data frame from it, fit some time series models, predict the future, and then output a forecast. What was happening was that this kind of pipeline was on fire for them, specifically, and then due to the operational nature of their role, they were also kind of time pressured and in a time crunch. So then my team came in, and what we found was, came in to help them, was that featureizing this data frame was where the biggest pains were, and this is where Hamilton started out. So just to give you, peel back the onion a bit, so why was this data frame causing them fires? Well, it's a very wide data frame. So it's on the order of thousands of columns wide. It's on the order of tens of thousands of columns, kind of rows deep. It's not big data, so it all fits in memory, but the main point is it's very wide. Why is it so wide? Well, columns just end up being functions of other columns, because that's how kind of featureization kind of works, especially when you're doing time series modeling. And what you get is this kind of successive chaining of columns being inputs to other columns, being inputs to other columns. And this is where, this is what was causing them a lot of pain. Just to give you an example of like why, where did this pain come about? Well, here I have some sort of example code written in pandas that should be kind of familiar to you if you know pandas. But essentially what it's doing is, you're manipulating a single kind of data frame, and you're creating and adding columns to it. And as you'll notice that there's many different styles that you can do this in. And what I want to tell you that, if you're doing small things, this probably isn't a problem. But if you scale to like thousands of columns in a growing team, you're going to run into issues. So why is that? Well, one, if people can write functions or create columns in different ways, then there's a lot of heterogeneity in the code base, very different expectations depending on where you look. Inline data frame manipulations are great, but how do you test them? Code ordering becomes super important. So you can't really just arbitrarily change things. You kind of have to really know the order to really understand what's going on. And what this really means is that the testing and unit testing story is pretty abysmal. Documentation is also very difficult. Code reviews become slow and challenging because you really have to understand what's going on. And then therefore onboarding and debugging are actually challenges in this code base. In short, the code for featureization was causing the Fed team a lot of problems. So Hamilton. So what is Hamilton at a high level is, as a user, you write functions, Python functions. Hamilton, you give them to Hamilton. Hamilton creates a directed acyclic graph or a DAG that models kind of the data flow of computation. You then ask Hamilton, hey, give me certain sets of columns. Hamilton knows what to do, and then, for instance, can create a data frame just with those outputs. As I said in the beginning, Hamilton's a new paradigm. And what I mean by that is you write Python functions, but in a specific way, where the function name is, say, an output column if you're creating a data frame, and where the function inputs then map to other input columns. And so on the right here, if you were to create a column C from some in column A and column B, you would have to rewrite it into Hamilton, where the name of the function, or name of the column becomes the name of the function, and the inputs become input parameters, and so they have to be named appropriately. We can make use of Python type hints to statically check things to make sure that functions line up, and then because it's a function, we can make use of documentation, the function documentation, to kind of document things. So how do we go from code to directed acyclic graph? Well, we kind of use the Python inspect module to crawl and find these functions. We pull the function names and parameters. Then it's just a simple case of graph theory 101 to create a DAG. To go from DAG to an output, we then you just need to provide what outputs you want. We then can walk the graph, figure out what inputs are needed, figure out the execution path. Functions are only executed once, and then they're combined at the end. So key point to remember is that with Hamilton, the function names and function parameters need to match if you really want to create a DAG. So for things to be stitched together, things really need to match. The second point to remember is with Hamilton, you don't actually have to maintain a pipeline. You don't specify at the end, like other systems, that, hey, I want to stitch these things together. With Hamilton, at the end, you just say, give me these outputs, and Hamilton does the rest for you. In one sentence, if I was to describe Hamilton, it's that it's a user-friendly data flow paradigm. As an aside, you might be wondering, why is it called Hamilton? Naming things is famously one of the hardest problems in computer science. And when we started this project, I was trying to go for associations with the Fed team. The Fed team reminds me of the Federal Reserve. What's something foundational about the Federal Reserve? Alexander Hamilton. And then it just so happens that, the Fed team at Stitch Fix models business mechanics, which has Hamiltonian concepts. And similarly, we're doing some graph theory stuff, which has, Hamiltonian concepts there. So I think Hamilton is a very appropriate name for this library. So let me show you some Hamilton code so you can get a better feel for what I'm talking about. So to use Hamilton, you essentially write Python functions, as I said before, and you stick them all into some sort of Python module. Here, we're calling it myfunctions.py. The salient things to note is that the function names, if we want to create a data frame, represent the output columns that we want to request. And then it's very easy then to see, what inputs each function require. And then also, in this case, know that if we want to compute spend shift 3 weeks per sign up, we need to compute spend shift 3 weeks, which is this function here, and so forth. So how do you go get a data frame? Well, you just need to write some code, what we call some driver code. Let's walk through it. So first, you need to set up provide some configuration, maybe some initial data. You then need to you need to import the Python module that you want to kind of crawl. You stick it together in a Hamilton driver, which creates the DAG. You specify what outputs you want, and then you execute, and boom, you have a data frame at the end. And then as bonus, you can also visualize things very easily. So if you want to know what the path of execution is, it's very easy to do so. So again, it is open source. You can go try it for yourself. I won't be offended if you drop off now to go play around with it. You should be up and running in 15 minutes. It's pretty easy to get started. So in short, what is Hamilton? It's a user-friendly data flow paradigm where users write functions that create a directed acyclic graph through function and parameter names. And then Hamilton handles execution of the DAG and creating outputs. So Hamilton is Stitch Fix. So after 2 years in production, it's been very successful for us, especially for the Fed team. So specifically, when we started out, the Fed team really wanted, a code base where they could, test things very easily. They had good documentation and a good development workflow. And by rewriting their code base into these kind of Hamilton functions, they got everything. And actually, I want to say we actually knocked it out of the park. So why was it a home run? Let's dig into that just a little bit. So say for testing and documentation, Hamilton forces this paradigm of, you request outputs and those outputs map to a single function. So therefore there's a single place to find logic. And then therefore there's only a single function that needs to be tested to kind of check whether that output is doing what it's intended to be done. Yeah. And then the function signature actually makes providing inputs very easy. So creating unit tests is very easy. And then because of the way Hamilton operates, it forces function names and input parameters that mean something. So code should be pretty legible and readable to anyone. And then because we're using a function, you can reuse the function doc as a natural place for documentation. And so therefore everything is naturally unit testable and everything is naturally documentation friendly. Hard to say that of many code bases. In terms of the workflow side, by writing these Hamilton functions, Hamilton also enabled the team to easily visualize computation, faster debug cycles, better onboarding and collaboration experience, and as a bonus, a central feature definition store. So from the visualization front, they have a data frame with 4,000 plus columns. How do you think about it? How do you visualize it? How do you explain to someone what's going on? Because we rewrite things into this Hamilton kind of way, it's very easy to visualize. So here I have a zoomed out view to obscure names on purpose, but the point is it's given no matter, it's very easy to visualize things and walk through them and explain to someone. And then you can also export. We create dot files, so you can put it into your own visualization, another visualization system very easily as well. Debugging functions are super easy. Say we have a problem with spend shift 3 weeks per signup, and we're trying to debug. We know that, hey, there's only one function that defines it, so we can go straight to the definition and look at it. If I didn't write this, it should be pretty understandable as to what it's doing, because either the function name makes sense and there's documentation. And then it's very clear and easy to see what the inputs are to this function. So when I'm debugging, it's either the bug is definitively in this function or it's somewhere upstream. In which case, it's very easy to methodically, recursively walk back through the DAG and continue my debugging process. The nice thing about having these functions in a Python module is that you can also import them into other contexts and play around with them if that's also your style of debugging. Collaboration is also super easy when you're writing Hamilton style functions. Specifically, it means it's really easy to assess impact and changes when the names mean something. So the function names and function parameters are pretty understandable. When you're trying to add a new input, it means you're adding a new input to a function. Okay, you can assess the impact of the DAG. You can see whether that input exists or needs to be provided. If you want to change the names of things, it's very easy to assess whether you've changed everything completely, since it's generally just a matter of search and replace. If you're adding a brand new function, you're not going to break anyone else's functionality because it's going to be a brand new node in a DAG that is independent of everything else. And then similarly, if you're going to delete code, it's very easy to determine whether you can. Net result is that code reviews are much faster and it's easy to pick up where those left off, meaning that if someone leaves your team or you are handing off, generally because things are documentable and testable, it's very easy for other people to come in and pick up things. So the Feds team gained a central feature definition store as a byproduct of using Hamilton, and that's because Hamilton forces you to organize your functions into modules. The way that the Fed team kind of uses this is that they each function follows a team naming convention. So for instance, D underscore prefix to a function indicates that hey, it's a date feature. So if you see it in any other context, that it's a date feature that's being requested. And then they organize it into thematic modules that better map their working style. So for instance, all date features are together in a single kind of module. And then this allows for them to kind of work on different parts of the DAG easily. And then because it's in a central repository, it's also versioned by Git. So it's very easy for the team to kind of create, find, and reuse features by the team. And then if you ever need to go back in time and debug something or recreate an output, it's very easy to do so since everything is versioned in Git. In case you don't believe me that the Fed team really likes using it, I got some testimonials. So first quote is from Danielle. the encapsulation, and she says this about Hamilton, the encapsulation of the logic in a single named function makes adding nodes, edges simple to understand, communicate, and transfer knowledge. So specifically in the context of, pull requests are easy to review, and onboarding someone to the team is very easy. Another quote I have is from Shelly. She says, I like how easy breezy it is to add new nodes and edges to the DAG to support evolving business needs. So in their case, say marketing is coming up with a new campaign and they need to account for that in their modeling. So then add a new feature for it. This takes minutes for them as opposed to hours before using Hamilton. So Hamilton and Stitch Fix, in short, like the impact that the Fed team had by rewriting things into Hamilton is that they gained naturally testable code, always, naturally documentable code, a data flow visualization for free, faster debug cycles, a better onboarding and collaboration experience with the bonus central feature definition store as a byproduct, and which with a net result of a home run for them. I'm actually going to claim that by using Hamilton, the Fed team can continue to scale their code base, so, go to 8,000 features or whatever without impacting team productivity. Rhetorical question for you all, is that true of your feature code base? So hopefully by now I've kind of piqued your interest as to should I look at Hamilton? And I'm just going to go through some tips to, to get started, specifically 5 things. So if you want to use Hamilton within your own ETL system, I want to say that Hamilton is compatible with any ETL system that can run Python 3.6. So Airflow, Metaflow, Dagster, Prefect, Kubeflow. If you can run Python 3.6 or above, you can run Hamilton. The recipe to do so is pretty simple. You just write your Hamilton functions, create some driver code to execute it. Then you need to make those Hamilton functions accessible in a way that you can run it in your ETL system. So either this means publishing it as a package, or saving it to repositories for it to be checked out. You need to include SF Hamilton as a Python dependency, and then have your ETL system execute your driver code however you usually do that. And then that's all you need to do. Pretty simple. The other is if you're migrating to Hamilton. So what we did at Stitch Fix, the Fed team was a pretty big migration. So what we did there to kind of help with that was we created a continuous integration system to make it really easy and frequently to compare results as things were going along. This helped to kind of diagnose bugs as we were going along. And actually, most of the time, it was actually finding bugs in their old implementation, not the new one. So what we did, the kind of workflow was we wrote functions, checked them into Git. Then we had a CI system kick off a job, which actually computed the DAG and then also compared results with what was in production. And then it gave us a scorecard with which we could know, hey, we've correctly implemented this thing or not, and then made iterating and keeping tabs of things that much simpler. The second is if you want to integrate Hamilton into your workflow, you probably want to write a custom class to kind of match your existing API rather than trying to make your workflow match how to call Hamilton. And that's because when you're migrating, you want to kind of avoid making too many changes. So I think focusing on just Hamilton functions and in a specific way will make it easier. Specifically, what I mean by that is that with Hamilton, you'll define your functions, which will create a DAG. You'll then kind of instantiate a driver, which will then execute it. Now, rather than trying to get your existing inputs to match and run Hamilton directly, write this kind of wrapper class, which will can match to your existing API inputs and outputs so that it's much easier to kind of just insert Hamilton in and then worry about changing this after you've done your migration. In terms of key concepts to grok, the first is common index, especially if you're creating data frames as output. Hamilton relies on the pandas series index to join columns appropriately. And so at Stitch Fix, what this means, the best practice was when you load data, you essentially want to ensure that data that's loaded has a common kind of spine or index that makes joining kind of just work as intended. And then from there, you can kind of continue with your normal transformations. Because the Fed team does time series modeling, what this meant was that each data input had to have a common date time index. The second is naming. So function naming, as I've kind of harked on, is pretty important with Hamilton. It helps you create your DAG. It drives collaboration reuse, and then it serves as documentation itself. Key thought is you don't need to overthink it. So you don't need to get it right the first time because it's really easy to search and replace, especially if you're writing things in a central repository. It's really easy to search and replace and change things as your thinking evolves. But it's something that you should converge thinking on, since that does help drive collaboration and how your team functions. The third is output immutability. So because functions are only called once, it means that you can generally kind of come up with a pattern where what it outputs is immutable. Now, that's only true if you don't mutate that output in another function. Specifically, say if you are operating over a pandas series and you get passed in one, don't mutate it, create a new one. Otherwise, your mileage may vary when you're debugging. So best practice here is to test for this in your unit test if this is important. Otherwise, clearly document that you're mutating inputs so it's easier for someone who comes across things to understand what's going on. Fourth thing is code organization Python modules. So functions are grouped into modules, and then use modules as input to create a DAG. Use this to your development advantage. So use modules to model team thinking. So in the case of the Fed team, they stuck things into modules that made sense for them. This helps isolate what you're working on and enables you to replace parts of your DAG easily for different contexts. Specifically, when you create a driver, you pass in a bunch of Python modules. You can kind of not include modules to change the shape of the DAG and what's available. You can easily kind of create shadow modules to replace things. So it's if you get the module structure right, it gives you a lot of kind of ability to kind of compose and change the DAG as necessary. Fifth is function modifiers, or also known as decorators. So what do I mean by that? You might see a Python function with an add above it. Hamilton has a bunch of these to modify behavior. So an example here is if you're loading data, typically say you're reading from a CSV, it comes back as a data frame. Hamilton works best by thinking in columns. So we have a kind of a decorator here that you could provide that will say extract the columns of the data frame for easier downstream use. So best practice here is to learn to use them because they do improve and increase functionality of Hamilton, and they also help to keep your code dry. And the Fed's team's favorite, for just in case you want to know, is @config when. Okay, so last 5 minutes or so, I'm going to talk about extensions. So why talk extension at all? Well, the initial shortcomings to Hamilton were that it's single-threaded. So it didn't run kind of in parallel in any way. And it could not scale to big data because it was, only could run on things that were in memory. You can only produce pandas data frames, and it didn't really leverage all the richness of the metadata that, we got when we created this DAG. So I'm going to talk about some recent work we did to kind of remove some of those constraints, and then talk about some future ideas that we're interested in exploring. So first is scaling computation. So Hamilton grew up with a single core in memory limitation, and this was a blocker to adoption for some. But our goal in kind of providing this capability was to not modify Hamilton code at all to scale. So if you're creating, say, a pandas data frame, things should just work. That's kind of the idea. What I mean by that is this code that I showed you before, we don't want you to have to change this code much at all to be able to kind of scale to bigger data sets and data sizes. Luckily for us, Hamilton functions are generally very amenable for distributed computation because they define, because everything's encapsulated in a function, we can distribute those functions pretty easily. And then just so happens, Pandas has a lot of support for scaling these days out of the box with various different systems. So with the 1.3.0 release that kind of we just put out, you gain experimental versions of running Hamilton on Dask, koalas on Spark, and Ray. And so the short of it is you can scale pandas out of the box right now. Why are they experimental? Well, they haven't been baked in production for long, so hence just a bit of a caveat that like, hey, this still isn't fully baked yet, but it does mean that you can kind of scale things very easily. Just to kind of give you an example of like, well, just how easy should it be? The only code you should really have to modify is the driver script. So here, you might have to just change how you load data into the system, just because, if you're using Dask, you want to kind of load it in a distributed manner, how Dask would like you to. You then have to instantiate a client, say for Dask or for Ray, or Spark context. We introduce a concept of a graph adapter. You instantiate one, you pass it into the driver constructor. Then as normal, you kind of request your outputs and execute, and that's so basically 4 lines of code to scale. I think is pretty cool. So custom return objects. As I said before, Hamilton grew up building pandas data frames. That's all it used to be able to produce. What if you don't want that? Well, in the 1.3.0 release, you now have control over what the final object can be. So for instance, if you want to return just a dictionary of outputs to some sort of object, you can return an NumPy matrix if you're doing NumPy things, right? Or custom objects, or even TensorFlow, PyTorch things, you name it, you now have control over it. Again, it should be pretty easy to use. And so you just need to modify your driver. Again, you kind of have to instantiate a graph adapter. A graph adapter can kind of take in something that kind of tells you how Hamilton should kind of create this result. Again, you pass it to the constructor. And then here, I'm actually requesting, hey, give me a dictionary of outputs. And then when you call execute, you now get a dictionary of outputs, not a data frame. Row-based execution. So what if you can't fit everything into memory, or you want to reuse your graph and call execute within a for loop with different inputs? Before you couldn't do that with Hamilton, or it was kind of awkward to do so. So in this 1.3.0 release, it enables you to configure a DAG once and then call execute with different inputs. So this enables you to, for instance, to chunk over data, you reuse the same DAG but pass in different inputs, and potentially opens up new use cases like image processing or NLP for being modeled within Hamilton. Again, just to show you, like, the only thing that changes here is the driver script or the driver code. You instantiate your driver, and actually to chunk over things, we now kind of expose an inputs option when you execute. So here you could load a data set, put it in a for loop, and then get different outputs depending on the input. So in short, as of the 1.3.0 release, Hamilton now scales for distributed and parallel execution with experimental versions of Dask, Koalas, and Ray. And it becomes a general purpose framework, since you can return any object type now, NumPy, PyTorch, dictionaries, you name it. And we also enabled row-based execution. So this gives you another a way to kind of chunk over data sets or process things like images or text. In terms of planned work, in no particular order, we're kind of thinking about, say, number integration. Can we include some notion of data quality when you're defining a Hamilton DAG, and lineage surfacing tools? So what is number? For those who don't know, it's a way to kind of compile Python code to machine code, or compile it to GPU code. And the task here would really to be, can we wrap these Hamilton functions and compile them for speedy graph execution? This means that if you're doing NumPy work, you should be able to get, according to number, very, very good performance gains. Data quality. So with Hamilton, we can do runtime inspection of outputs. Can we incorporate some of these expectations like Pandera? So Pandera is an open source kind of framework for doing so. Here I have a kind of a mock API example, but say you have some important output that you want to kind of check for. Maybe there's a way that you can tell Hamilton, like, hey, when you run this, check the output, and like, here are my expectations. So we're looking to, like, how can we kind of include that into the Hamilton framework? The other is lineage surfacing tools. So say you want to ask things of the metadata we have. The task here is like figure out ways of, what are good ways to expose information. You might be interested in this if you, have PII or GDPR and you need to kind of understand your exposure or where things are used. I mean, because with Hamilton, we kind of have, column level information of like how data is used in a data flow. So can we expose that? Can we help people answer those questions? Similarly, if you're developing with Hamilton, maybe there's a way that we can leverage it to tell you, like, hey, if you change this, these are the downstream impacts. And then because we know that, hey, if things are checked into Git, maybe we also know potentially who you should talk to kind of notify, or if you want to make changes to a DAG. If you're excited by any of these extensions, do go and like thumbs up, love them, because this will help, figure out where potentially we should prioritize our time. So in short, to conclude, Hamilton is a new paradigm to describe data flows. It grew out of the need to tame a feature code base at Stitch Fix. And we believe, or at least I believe, the Hamilton paradigm, provides teams with multiple productivity improvements and can scale with code bases without a loss of productivity. And with the 1.3.0 release, it's now a scalable general purpose framework. Thanks for listening. Would love your feedback. Pip install SF Hamilton, star the repo, create issues, vote on issues on GitHub. And then if you want to join us on Discord, we're curating a community there and would love to have you. Thanks. Happy to take questions.
So I'll read
a lot of information.
Some people were putting in the chat, like, I didn't realize I put it on 2x.
Oh,
right now.
I'm sorry for the people on YouTube who wanted to come back and watch it at 2x.
Yeah, exactly. You're just going to hear. Anyway, there's some awesome questions that came through. One, actually, there was a good discussion going on around like how lightweight Hamilton is. And so that's something cool that's happening. But then there's one that just I should probably bring up because we are talking about feature stores so much. And does Hamilton work with feature stores like Feast or Tecton?
Yeah, so Hamilton doesn't tell you where you should materialize or store your data. So you could use Hamilton as a way to compute things, and then it's up to you to push it to, Tecton, Feast, you name it. Like Hamilton isn't opinionated as to like what the actual store is. It's just a way for you to kind of define the computation that you want to happen to create a feature.
Nice. And this is a really cool question too. So Javier is asking, so Hamilton connects with Dask. In my view, they perform a similar task. What are the differences there?
I mean, it's just mainly the API, right? So like with Hamilton, you're writing these things in this Hamilton function. And so you kind of define your data flow graph by writing these functions, in which case with Dask, you would have to kind of annotate and do all that manually. You would have to basically have like a pipeline step that would say, hey, take this input, put into this function. But with Hamilton, we can do that for you.
Oh, nice. All right. And then this is another great one. How does Hamilton handle duplication, i.e. creating the same data with different names?
Those right now get created fine. It's Hamilton does catch the case if you have multiple functions defined and you try to create a DAG with them, but it right now doesn't have any capability to catch that case. If you name functions, if you're creating the same output but named with different functions, Hamilton doesn't currently catch that.
So the other thing that I will mention to everyone, if you have not seen it, there's a great blog post on Hamilton when you guys open sourced it. It's really informative and it helps. There's a lot of people that looks like they want to go test it out and have a play with Hamilton. So hopefully that works. Go see the Discord community and say hi to Stefan. Thanks, man. This was cool.
Thanks for having me, Demetrius. Likewise.
Yeah, and everyone else that didn't get their questions answered, I think Stefan and another one of the Hamilton co-creators are in Slack answering questions right now. So jump in there, ask away. They'll be telling you all you need to know about Hamilton. So we're going to keep cruising. We just got more great talks. And we also get to give away some swag. Yes, I'm going to give away a little more swag because there was a hilarious photo that was shared just a minute ago in the Slack channel by Alex Carney. So Alex, if you are still on here, reach out to me because you win some swag. That is just an epic photo of your little birds looking at the frog. And I want to remind everyone, I think I mentioned it before, but we've got that survey. Fill out the survey. Let us know what your war story is. We'll be giving away more swag and awards for the best and worst war stories. The other thing is now you get to vote. You get to vote on what we're going to do in the next break. The break's going to be 10 minutes, so you can go and make a tea or whatever it is that you're doing in your time zone. And I am either going to lead a meditation or I'm going to play the ukulele. All right. And I'm not going to do both at the same time. I know some people wanted that, but that will be for the May event. So vote. What do you want? Do you want a meditation or you want the ukulele? And I will ask for an improvised song. So you all will be feeding me the lyrics for the ukulele song. That is going to be in the next break. All right. But before the break, we've got some cool stuff. We've got another great talk. Eric is around, I think. Eric, you here? Can I page you to the stage? There he is. What's happening, man?
Hey, how are you?
I'm good. I'm very good. So Eric, I just got to tell you, since we spoke last, I keep running through my mind. I think Eric, you blew my mind when you talked about the symptoms of too much centralization or too much decentralization. I loved that. And I encourage everyone who is here, if you like this conversation or if you like the presentation from Eric, go check out the MLOps community podcast that he was on, where he talks about centralization versus decentralization. That's it, man. Eric, I'm going to let you take over. It's all yours. And you can also vote at the end for if you want a ukulele or meditation.
I don't know
See you
what I
later.
want.
They both sound so good.
I do like ukuleles, but yeah. So just I'm gonna see if I can just quickly share my screen. Sorry, so was this like awkward? 3 seconds. Do you see it?
Oh yeah, looks good.
Thank you. I kind of didn't name this talk super well. I think I originally called it data engineering isn't software engineering, but then like I realized like what I meant is more like it's not like other types of engineering. And then like B, I call it data engineering, but I really think of like, data engineering, data science, machine learning engineering as like sort of adjacent field that share a lot of these traits. Anyway, so that was enough sort of preface about the title. By the way, Demetrios, like feel free to like interrupt me as much as you want to. I don't have like a ton of stuff. I'm Eric Bernhardt's son. I spent a lot of time at Spotify where I built the music recommendation system, did a lot of machine learning. I also done a lot of business intelligence, a lot of data engineering, data plumbing. I've also been a CTO for many years. Like I've done a fair amount of front end and back end and led a lot of different teams. Now I'm working on my own thing, which I'll get back to a little bit later. But anyway, so can I see the chat? Oh, okay, big fan of Eric. I wanted to talk a bit about like different sort of types of engineering, and I think my sort of like theory is like there's a lot of like traditional types of software engineering, and like a lot of the sort of tools and best practices in software engineering, like people sort of automatically think like, why, data teams need to be more full stack, or, data teams need to adopt those tools. And like my theory is like, there's a reason why those tools and best practices exist. And there's a reason why some of them might work really well in the data world, but some of them might not at all work well. And so, just to sort of kind of take a step back and, sort of putting on my CTO hat, sort of a lot of traditional software, this is very crude generalizations, by the way, like most of my slides, will be very, generalized a lot. But like, I think about like backend engineering, like traditional software engineering, it's like kind of like, you're writing like business logic, and it's kind of like rules, you have like, if order value is more than $100, then shipping is free. You write a unit test for that, you make sure it works, and you kind of deploy it, into a container, and that container runs in the cloud, and there's like, web traffic hits that container, and that container kind of stays there until you replace it with a new container and things like that. In the data world, a lot of these things like do not apply. Like we're not shipping rules to start with. And we're often shipping like very sort of fuzzy things. Like it could be like a machine learning model. It's like hard to know, does it work, does not work. It can also be like insights, You have very sort of weird sort of hardware requirement. You have a lot of like bursty scalability. You might need 100 machines for a little bit, and then like scale it down to 0, and then scale it up again, and then scale it up. So I think it's like kind of useful to think through like, okay, what is the set of assumptions in the sort of traditional software engineering world that led to the like tool chain that exists at, today? And what of those are different? And like, maybe that means like, we shouldn't use the same tools, and, we should have different workflows and different processes. And like having coded I've been coding for 30 years and, professionally for 10, 15 years. I think it was worth like thinking about like, how much this has changed. Like when I started coding, like, cloud didn't exist. Containers didn't exist. Like, a lot of sort of how we work with version control and other things like was very different. And I just, there's still like a lot of controversial ideas. So this just goes to say that like, I think best practices are always like sort of moving target. Like it always keeps changing, and sort of, new tools emerge, and then we adopt them, and then, things sort of organically mutate over time. I think a lot about, okay, like, again, like being a CTO, like, okay, like the goal, I think to some extent for software engineers, like, we want to build the right tool, like we want to use tools that makes us productive. And, what does that mean? What I mean with productivity is almost impossible to measure, but in some way I mean like shipping business value, which is, I don't know, it's very hard to put a number on that. What I've seen though in practice is that productivity can be quite well understood if you think about the sort of the feedback loops. And what do I mean with that? I think kind of walking you through a couple of different examples might sort of help understand what I mean with like fast feedback loops. I was actually doing some front-end development the other day, and I don't know if you've been like doing front-end development, but like to me it's like mind-blowing. Like you like write some code. I was using Vite, and it's like auto reloading like React component. It just like shows up in the web browser like seconds later. And you know, something like very like visually gratifying, but like, you know, that like feedback loop, right? Like you're just like hacking on stuff and it like shows up and it's like hack. And then, you know, there's a slightly longer loop when you maybe create a pull request and get feedback and things like that. But like generally, I think, you know, there's something like very, you know, enjoying, you know, it's a lot of fun to do front-end development for that reason, like because the feedback loops are very tight. Back-end engineering, like, yeah, like, you know, still like, you know, pretty good feedback loops. You know, you write some code, again, you know, if order value is larger than 100 and like, you know, shipping is free. By the way, like feel free to interrupt. I'm just like talking a lot. So feel free to like ask questions in the Slack or anything. I'm keeping an eye on it. But like generally, like I think the sort of the main tool that's emerged for backend engineers to validate something works is running unit tests. You can run one unit test, you can run many, you know, et cetera, and then you sort of merge it. But like through unit tests, that's like the other way. Like for backend engineers, you get this like kind of fast feedback loop. Now for like analytics engineers, it's a little bit different. Like you read like SQL queries, and you know, you run them, so just get syntax error, like whatever. But it's also like there's something like kind of like nice about that feedback loop. You sort of write code, you know, SQL, like you get a result, right? And then you look at it and it's like, oh, does it answer your question? Like, no, okay, then I keep iterating. For data engineering, and by like data engineering, again, like sort of bunching together a whole bunch of sort of adjacent field, like data science, like data engineering, machine learning engineering, a bunch of stuff. I feel like something here is broken, right? And you know, and granted, like everyone's like feedback loop workflow is a little bit different. And this is sort of, you know, very crude generalization. But I don't know about you, but like every time I like want to do something at like scale, I have to like spend like 3 days like writing YAML and like wrangling with like AWS and Kubernetes and like containerizing things. And my brain just explodes because like all I want to do is like write something and like see if it works or not. And I think that's bad. And, you know, I think a lot about that. Like, why is it, you know, is there something missing? And I think part of it is like, we're using tools that were sort of optimized for a different domain. And here's like a very terrible scorecard I wrote. I just very subjectively put in numbers here, kind of thinking through these different fields or these different tools. For traditional software engineering, you know, you look at like the top 4 rows, maybe, you know, or and I don't think it's a coincidence that Kubernetes is actually quite popular. Like for the types of challenges that, you know, exist in, you know, especially like backend engineering, you know, like Kubernetes is quite good. And, you know, but however, like what if like you remove the top 2? Because like they actually don't really matter. Like if you're running data stuff, you know, for some people, you know, the third one doesn't even matter. And like suddenly, like, I don't think it's like so surprising that like data warehouses have been, you know, taking a lot of sort of, you know, it's like people don't really think about like data warehouses as versus like Kubernetes. But I actually think, you know, there are some similarities, like they're both runtimes, like in terms of like running logic. And you know, I don't think it's so surprising, like in this sort of view of the world, that you know, data warehouses like doing a lot of, taking a lot of more, you know, taking over a lot of sort of traditional data workflows. Anyway, this is what I'm working on. So I'm working on this new sort of way where I truly think there's a way to get the best of almost all worlds. Some way to like have that sort of dev prod, like the sort of same type feedback loop, but you know, with the cloud and like with scalability and all those things, and with the ability to write arbitrary code. So stay tuned. I haven't launched anything on it, so I don't even have a website, but it's an interesting field, and you know, definitely feel free to, you know, follow me on Twitter and my blog, and you know, see what else I'm working on. this is kind of quick. I don't know, Demetrius, I'm happy to spend a little bit of time, talking about this, or any other questions from the group.
Yeah, I get the feeling we'll have some questions coming through. I've got some questions for you. It's not perfectly related to this, but I did read your blog posts about some predictions that you have. And I wanted to talk to you about that while people are scurrying to ask questions. So, as a little background, in case anyone does not read Eric's blog post, highly recommended. It's at your website, right, which is on the screen. Now, can you tell us about this blog post and what prompted you to actually write something like that? And there are a few hot takes on there.
Are you talking about the most recent one about the cloud, right?
Yep, exactly. About
Yeah.
AWS, like not going up the stack anymore.
Yeah, I think there's a lot of different like entry points into that blog post, but like one thing I've thought a lot about is like, I think we're actually quite early in cloud adoption. Like we obviously like had, it is modal, by the way, with an A, just to answer the Slack the message. But so go back to your question. I think we're quite early in the adoption of the cloud, and I think one question I always ask myself is like, in this era of the cloud, like, why I was still like provisioning cluster, like thinking about resource management, and like to me, like the inevitability of the cloud is like you have infinite resources. Like, computers are very good at like packing things and estimating. Like, why can't the cloud just take care of all of that stuff for me? So to me, like the inevitability of the cloud has always been serverless. Now the question is like, okay, why is serverless not more prevalent? And I think a lot of it comes down to like, the first version of serverless tools like Lambda, it's just not good to work with. It's just like kind of does not like fit with like the sort of, and a lot of it I think goes back to sort of what I talked about with feedback loops, right? Like writing a Lambda and like executing it has this like super annoying feedback loop, right? Where you have to like write some code, build a container, upload that container to AWS, then go into AWS and like wait for that container to be like fully whatever it is, like they do something to it. And then you like trigger Lambda, and then like, a minute later, the Lambda crashes and you're like, oh, I have to go into like a tab and look at the logs. And then it's like, oh, the exception is there. And now it's like, and maybe you have to set up some CloudWatch stuff. I don't even know. But then you have to like go back, then you can go back and like, okay, now I'm going to like write some more code. And this is like this like awful programming experience. So I think for that reason, like I've been thinking a lot about like, what is it that, what is the true sort of end state of serverless? And I think when you look at the, back end and front end development, I think there's been a couple of really interesting companies, particularly like Vercel, who's like, basically saying, or, on the Jamstack side, Netlify, Cloudflare Workers to some extent. There's some interesting database companies, like obviously Snowflake and Mongo, so the traditional one, but then there's like PlanetScale, Yugabyte, et cetera. And they're sort of taking databases and just making them like serverless. And like, I think to me, like there's a set of vendors that sort of are emerging like at a layer above AWS. You have like AWS, GCP, Azure as like the sort of foundational sort of hardware layer where you can like rent capacity in them. And then there's a set of vendors like at a layer above, that lets you not have to think about all this like resource management and just like lets you use a database. And that's where I think we're going to see a lot of evolution in the next 10 years. And sort of my prediction with the blog post was that I actually think AWS is pretty happy to stay in the lowest level because they're very good at it.
Yeah. So my only thing with that when I read it the first time was I just have a hard time seeing AWS with their infinite resources saying, all right, we're going to lose this one. Let's just put a fork in it. It's done. And we'll stick to what we know best. Like I do understand, especially when it comes to AWS, you've got so many different services that they offer and so many acronyms and all that. But at the end of the day, and all of these are really trying to drive this compute and storage, I just feel like for AWS to put up the white flag, or any of them for that matter, GCP or Azure, it seems really out there to me. But I want to hear your take. Like, how do you think that they would just say, see you later?
No. I think, first of all, I think there's so many different internal teams in Amazon. It also depends on like who you ask, right? But like, I think it's like interesting to look at Redshift versus Snowflake. because like AWS like kind of had the opportunity to create Snowflake, but they didn't. And the question is like, why didn't they? Like, why didn't they like take, and they actually like finally sort of released a version of Redshift, which is kind of looks like Snowflake sort of architecturally, just a few months ago. But for a long time, like Amazon had, was the only provider of, truly scalable cloud native data warehouse, right? But the sort of interesting thing about Snowflake is that Snowflake, let's say a customer is already on AWS, and let's say they're considering, should I use Snowflake? Should I use Redshift? I don't know. And let's say they use Snowflake. Yeah, like AWS, they won't get the money now for Redshift. But as it turns out, like Snowflake, they will want to run it on, in AWS anyway. So AWS will still make money from, the CPU and the storage, right? The storage is S3. And so for AWS, it's actually like the math actually kind of isn't so bad. Like even if they lose business from Redshift to Snowflake, they actually end up getting a lot of that money back. The other thing is like now they completely outsource R&D and sales and marketing to Snowflake. And so I don't know, if you look at the math, like, it's actually like not clear cut. Like, it's not like evident that like necessarily like AWS is worse off, losing business from Redshift to Snowflake.
Yeah, actually, as a friend of mine who worked at AWS said, the house always wins. And so
what does that mean in this context? Who's the house?
The AWS is the house. So they're getting the
I see what you're
saying. Kickback, right? They're getting money from it. So it's great. Totally. And I like this thought that you just mentioned. AWS is outsourcing their R&D to Snowflake and letting those people do the heavy lifting. That's an interesting one that I hadn't thought about. So, all right, I think I can say it now, but wait, I'll wait a sec. But there's a little bit of a surprise because somebody was asking for it in Slack, and I've got a surprise for us in like 2 minutes. But I want to ask some of these questions that are coming through in the chat. One of them being do you think Rackspace is moving up the stack?
I really don't know Rackspace particularly well.
Okay, so no worries. Then we can skip over that one. Oh,
I do think like, in a way, like stable oligopolies are quite good businesses to be in. And like, if I look at like cloud vendors today, I mean, the three big ones are, by far AWS, GCP and Azure, right? And I think there's like a long tail of like smaller vendors, but I think my expectation is like they're always going to be niche.
Yeah, I see that. So here's the surprise for us. Somebody asked in Slack, can we rehash the Mike Eric podcast that happened on the MLOps community? And so I pinged Mike. What were you sleeping, Mike? You were.
No, I'm sitting. I'm honestly just sitting on my couch watching Apply, and so then
I can't believe it. We pulled him back up here. We got him. We've got like 10 minutes to chat. You two get to. I'll moderate a little bit, and I'll throw some questions your way and figure it out. Right now, the most pressing thing on my mind, I think, is. And both of you just gave a talk about certain aspects that you feel in the landscape, the current landscape, how you see things, what you're focusing a lot of brain power on. But are there other parts of the landscape, and Mike, maybe you can go first on this one, that you also are, it takes up quite a bit of brain energy, but you're not actively making anything for it? Like, is there something that you feel like, oh, there's this over here, but
yeah, for sure.
Not right now.
So there's nothing is perfect yet, but I was just thinking about like, the conversation Eric and the three of us essentially had for an MLOps community, which I guess we could go watch again, but I don't even remember exactly the topics we covered here, but just kind of following up on something that Eric was just saying about, adopting the cloud. I see that as still a thing a lot of people are struggling with. It's still really hard. There's, that's a thing for us at at Tecton, where we have a lot of people who want to use, they want to use Tecton, and it's, they may not be fully on the cloud, and that's just for a business decision for us. We don't want to do anything on-prem because we're kind of building for the future, but it's exposed us to the challenges of adopting the cloud, and that has been a thing that it's a very messy process. And it's not like nobody's trying. There's, if you talk to every major cloud vendor has major investments in helping people adopt the cloud. I mean, Eric, I'm sure you've dealt with every different variant of this. And then even like companies like Snowflake and Databricks, which are not cloud vendors, but they're such major businesses that live only in the cloud, they are also putting in like significant effort into helping on-prem businesses find success in the cloud. And so that's kind of like that's kind of like that symbiotic relationship between those kind of cloud data platforms and the cloud vendors, and then like vice versa. It's to AWS's advantage to just have someone use a cloud data platform, whether it's Redshift or Snowflake. That's great. And so, there's that kind of like duality there, which makes for a nice partnership between them. But I think like that cloud adoption is something that we see really stinging a lot of major organizations still. And I guess like Eric, maybe a question for you. Why is it so hard? Like, what are the biggest elements there that are like still unsolved?
Yeah, and I want to jump in right before, sorry, Eric, hold that thought, because I think I saw a tweet that you sent out, Eric, and it was like something along the lines of, when I was CTO, I never thought about like, oh, like everybody talks about this vendor lock-in or like cloud lock-in, but the last thing on my priority list was, oh, I need to go and just lift and shift from AWS to Azure or that kind of thing. That's just something I wanted to pipe in with. But Eric, yeah, feel free to answer Mike's question.
I'll answer your question too, because I have more stories about that one. I feel like that sort of fear of vendor lock-in, like it's like, let's say you're like building a big office, for your headquarter, like would you be like, oh, I don't want to like lock in a contract with the landlord because like what, it's like, so like, I don't know, like I feel like this, like, I'm glad in a way that there's like a small fraction of like crazy people who like build multi-cloud system so that like everyone else like don't have to do that. Because like the fact that there was always going to be like some tiny fraction of people doing it, I think is a terrible idea for them. But the fact that they're doing it means like, cloud vendors' prices are always going to be like roughly in sync, right? Like AWS and it's basically what I said earlier. It's like a stable oligopoly, right? Like there's like three big providers, and this is sort of tacit price collusion, I think, in a way between the three. Like no one's going to start a price war, but on the other hand, like no one's going to like jack up the prices either. So you're going to have this like pretty stable price structure, which means that it also means like it doesn't really matter. Like there's no like, why would like they like jack up the price for for you, like because then they have to jack up the price for everyone, and so I think there's always going to be sort of price parity like roughly between the three, and then for that reason like it doesn't really make any sense at all to try to build multi-cloud.
So Eric, I've seen that certainly be true for like smaller companies where it's like, obviously there's a huge overhead for building on two clouds, and but I've seen larger companies certainly be able to leverage that threat where they can say, look, we've also built enough on Azure, so we could switch over to Azure. It would be, a 2-year effort for us or something like that. But, if it's going to save us $200 million, we'll definitely do it. And, that's that small number of players, of very large players that have that realistic threat of being multi-cloud or migrating between clouds, that is bringing that pricing parity for everybody, which is super nice.
Yeah, and I think that's
we all get the benefit from it.
There's like some small set of people that do that. By the way, like I think even for a lot of those people, it's not a credible threat. Like, to be honest, because like you just said it, it's like a 2-year effort. like as a CTO, like it sounds like crazy to me to spend 2 years to move from one cloud vendor to another to save money. Like unless you're like, burning, which like is like true for like very small set of companies, but like for most companies, like the idea of like spending 2 years moving from one cloud vendor to another is insane.
But I think, I mean, just consider that like that could be insane for a technology company where as a CTO, you're all about building the core capabilities of the business, right? And you're like the company is an engineering company building more technology. And so that kind of translates to, all right, let's stop the business for 2 years. But a lot of companies, they're not technology companies. And like the technology division is just like, running a lot of the back office operations, and it's not a revenue driver. And it's just a matter of like, all right, well, it's a cost, it's a cost center. Okay, let's move to a cheaper area. And I think that's where those threats become more realistic. I don't know of anybody who's actively building, their technology product and trying to build it in ways that will work in multiple clouds. I agree with you on that.
Yeah.
Well, let's kind of like play off of that, because something that I've been thinking about lately is how you have these really well-defined use cases for machine learning, and there are companies like AV, or you have like fraud detection, and you have those use cases that are seeing value in the companies. And then you have other like technology or AI first companies that the business is built around machine learning. And so they're also really interested, or they live and die by machine learning. And then as far as the market goes of other people that are using machine learning, you have this like long tail of other companies that are using machine learning or trying to get into machine learning. How do you all look at that as you're building your new tools? Is it something, I mean, Eric, I don't know if you're specifically building something for machine learning. I don't think you are, but I imagine that when it comes to data and the maturity of data too, like that long tail, there's a huge amount of companies that are doing stuff and maybe not proven out the machine learning use case yet, or just their way of working. And so, Mike, I'll shoot this over at you first, because I'm sure that you think about this, like that long tail. What does that look like, and how do you think about that?
I'm sorry, I didn't get, there's a long tail of use cases, but what about them?
So basically you've got like, you've got those long tails, but how do you look at them? Like when you're building Tekton, how do you think about like, oh, should I be trying to, because I imagine, and we've talked about this before, I know in prior podcasts where you're talking about how a few people think that they need something and they're not really, they don't understand what they need yet. And they're asking for the faster horse. They're not asking for a car. And so when you have these long tail, like how do you look at building a product around that where it's really vague and unclear?
I think it's for the like building a vendor product. It's the same as if you're like the CTO at a company and you're trying to figure out what does your infrastructure that you're building need to support, and you have a variety of use cases, and some are more important than others, and some are more similar to others and some are more unique, right? And I think in terms of the long tail, there is like long tails that are, that can mean different things, but some is like people with wacky requests that are super unique that are not really justified. So you can think of like the long tail of what are people requesting. And, I've had, when we were at Uber, I just remember one of the VPs saying, hey, we can't use Michelangelo because we need real-time unsupervised reinforcement learning, with like 3 other adjectives there. And I was like, not really sure that that's a thing, but that's one of those really out there requests. But then there's also the long tail of like real use cases, different use cases actually have real requirements. And so it's important to be able to distinguish between the what people are asking for and the true requirements, and then being able to help those people who are asking for the faster horse map to what their real requirements are. That's something that we spend a lot of time on, and helping understand what are people asking for and what is possible. And then designing and just having like very good internal discipline about, well, we don't want to support things that are not a certain level of reusability unless they provide a certain level of value. So that's just how we think about it at Tecton. But I think it's probably similar for if you're building a platform, internally in a business as well.
I have pretty similar experience. I think, I spent many years in the mortgage industry, and talking to a lot of like traditional mortgage companies and or talking to people who are like doing due diligence on, in the space, like they would always be like, so tell me about the magic AI machine learning brain that's like doing underwriting on the customers. I'm like, well, first of all, legally, we can't use machine learning to underwrite customers because that's against law in the US. But second of all, like, yeah, we use a bunch of machine learning, but it's like in completely different places than you would expect. And so I think that's, I think that's interesting, right? Like in a way, like, the bet in, investing in like AI technology or like tool chains is a bet that like, it will become more prevalent and a lot of more companies will adopt it for more places, in more places of the business. But yeah, like my experience is like those places may not at all be where, business people think, the value is like, cause, and like, by the way, 3 years ago, like, people didn't know anything about AI or like whatever. There was like chatbots and like whatever, but yeah, and it's like so interesting how like, I never actually seen like any single chatbot project like actually succeed. And so, but I've seen many other like, search relevance, like, recommendation system, it's so interesting how like, the sort of use cases that people think they need versus, what actually drives value is like so different. And I think that's, and maybe that's what you touched on, Mike, like there's just so much work on like, sort of also like working with people and like identifying those things.
Brilliant. All right, guys, I got to kick you out. This has been awesome.
Thanks for bringing me back in here. I'll just go back to being on my couch as a viewer.
Yeah, this was cool. This was surprising. Like, I'm glad that this happened. It was very spontaneous. And thank you for the person who recommended we do this. I think it was Prasad. Thank you, Prasad. We got to get you some swag. Reach out to me because that was a great idea and we appreciate it so much. So thank you, Eric. Thank you, Mike. I'll see you all later and we're going to keep cruising. We got more cool stuff to talk about. All right. The next one, and I know I keep saying this, that we're going to vote. We put a vote up in Slack. If you didn't vote already, get on Slack and vote. It looks like the ukulele jam session is winning so far, but it's never too late. I voted for the guided meditation, but I'm okay being outvoted. Get in there, vote if you want for the next one. We've got basically, I said this for the last 3 times, so I jumped the gun a little bit, but after this talk, there is a break. It's going to be 10 minutes. You can go do what you need to do. I'm going to probably be playing ukulele. It looks like the ukulele is going to win. Vote though, make the meditation win. And next up, we've got 2 speakers. This is Ed and Guy, paging Ed and Guy to the stage. How y'all doing? What's happening, Guy?
Hi, thank you for having us.
Yeah, what's going on? How are you?
I'm good, thank you. It's a bit late here, but it's a pleasure to be here.
Yeah, and there's Ed, right on. Well, you all are going to talk to us a little bit about Redis, if I'm not mistaken. So I am going to get out of the way. I'm going to let you all present. And then I'm going to come in with some sweet ukulele tunes once y'all are finished.
I bet it will be amazing.
All right.
Thank you. So again, thank you for having us in this session. I'm Guy Corland. I'm the CTO of Incubation in Redis. And with me, I'll present you. Ed is the Senior Product Manager and responsible for our AI machine learning initiatives in Redis. Ed will run the slides and will join and present the second part of it, and we'll show you what can you do with Redis. Thank you, Ed. Switch, please. So what are we going to talk about? We're going to talk about why using Redis as your real-time online feature store. Ed? So I guess most of you or all of you are already familiar with Redis. Redis is an open source in-memory data structure store. Mostly uses cache. I guess most of you know it as the default go-to cache solution or as a message broker. But Redis is more than that. Redis is being used lately as a database. It's been used so much as a database. It's so loved because of its simplicity that it was picked in the last 5 years as the most loved database by the Stack Overflow community. 5 years in a row. Right? More than that, like Redis is being downloaded by the billions. It's the most downloaded pulled database on Docker Hub, more than billion. In fact, it's more like 4 or 5 billion. Like Docker Hub just don't show you the number, but it is being downloaded by millions every day as the most loved and most used in-memory database. Okay? But a bit about us, like we are Redis, the company Redis, the company behind Redis, the open source. We are, as we said, the home of Redis. We are developing, maintaining, extending, and contributing to Redis in general and every ecosystem or many ecosystem product around Redis, the clients. And in general, we are keeping the Redis community happy and alive. We are really welcoming every open source contribution. This is a very open community, but obviously the company is also having its own commercial version called Redis Enterprise. It's like, and I'll you know what, I'll cover it later in the next slide, but we also offer an hosted solution for Redis. So like click your own, like click and get your own Redis offered on every major cloud, Azure, AWS, GCP. And we are already have like more than 8,000 paying customers across the globe using our product on the cloud, on-premise, Redis Enterprise. Ed? But what is Redis? Like, let me go deep a bit about Redis and explain you more about what is Redis and what is more than like why we call it a database. Like Redis, as you know, it's probably what you see on the left. Like it's different data structure. You can store very nice different data structure, like about 10 different data structures, strings, set, hash, bitmaps, lists, even interesting data structures like streams and hyperloglog. But it's more than that. You can use Redis using these modules on the right. These are like extensions that you can deploy on Redis. Also being maintained as a source available. You can go on GitHub, see the source, play with it, contribute, open issues, also manage as an open community. And this way you can get much more from Redis than you might expect from Redis as a simple key value. You can store JSON, documents, like you might store on every big data solution. You can even index them using some Redis search, doing some secondary, full text search, numeric, geoinformation. You can even store graphs, full graph database, like you might expect from any database, time series database. The nice thing that we are also focused on is how you can enhance your logic by shifting your business logic into Redis. This way you can even get much better performance with using gears, or even more probabilistic data structure like Bloom filter, Cuckoo filter, and many more. But on top of that, we are providing as a company, this is the commercial product that I described before, the Redis Enterprise. Redis Enterprise is what you would expect from any enterprise product probably when you want to take the open source experience and start to deploy it in production or stop care about all the management tools. So you'll get automatic linear scalability, high availability, durability of your database, obviously some backup and restore capabilities. And the thing that we're most proud about is you can do geo distribution. You can really have like 2 sites far away, fully replicated and active and doing some self conflict resolution. On top of that, you will get all the other stuff that you might expect from any database, like multi-tenant or security. But I think if you like take one step back, we're if we are seeing this pattern, like if in like 20 years ago, the most adopted database, what everyone would expect from a database was a relational database, and obviously Oracle, IBM, Microsoft were the leader back then. Then like 10 years ago, with the boom of NoSQL and all the other solutions, you would have seen like MongoDB, CouchDB, even Elasticsearch, Cassandra. You will see all these NoSQL database, document database popping out. We believe that in here, like in these 10 upcoming years, you will see this boom of open like Redis in-memory database solutions, because you do need to provide a low latency solution for your user. You need a real-time experience. And this is why we are here. We are talking about real-time experience, and this is where we think Redis is shining and almost the only one who can provide this low latency solution. And why do you need this low latency, such a low latency solution? Ed? So today, everyone expects like a real-time interaction. They expect like a constant experience, less than 100 millisecond experience. You expect to go to this website or open your application and feel a smooth experience, an instant experience, less than, and the numbers are talking about less than 100 milliseconds. And we're talking about everything, including AI, including like real-time inference. When you have a user interactive application, the user need to feel a smooth experience, even if you have a huge amount of business logic running behind it. Even if you push a lot of data into your application, you want this data to be pushed to your client almost instantly. Okay? And for that, you need a database that can interact with your application or ingest data in a sub-millisecond experience. So even if you already, like for example in AI, you already trained your model to be very, very fast, and it takes like half a millisecond to do the inference or to react on the user interaction. If your database does not react in a less than a millisecond, you're probably not going to be able to provide your end user the less than 100 millisecond experience, because usually your application will interact with the database a couple of times. You also have the internet latency between the user and the application. So summing it all together, you need your database to be very, very fast, less than 1 millisecond. If you're going to use this traditional database that provide you like 10, 20, 30 millisecond latency, you probably won't be able to provide this less than 1 millisecond latency to the end user. And the whole user experience will be damaged. So for that, you need to make sure that the data interaction, even with your model, with your application, everything is kept below 1 millisecond. And this is why, Ed? Oh, thanks. And this is why we think Redis is the most suitable database for online feature store. Like when you need your inference to be low latency, when you need your inference to be real time, like for example, user interaction, maybe video processing, everything that needs some low latency inference that includes some data that you need to take your model, grab some data and do some low latency inference, then you must have this low latency database. So Redis is there is amazingly suitable for that, doing low latency inference and high throughput. And it comes with extra capabilities that might help you do this inference in a better way. For example, it comes with a data structure called stream. So like you might do in other platform, you do some stream processing, you can now do it in Redis. So you can use Redis stream, do this low latency inference and stream processing, and immediately store it into your online feature store and immediately use it into your models. So everything resides in the same thing in memory, does not move between infrastructure, does not move between database. So you can really go into this sub-millisecond latency. On top of that, as I said before, you have other data structures. So maybe you need for your model or for your online inference a more complex data structures. So you have all of them there. You can put a time series data. So you can do like, maybe you want to retrieve a data that scaled for the last hour or something like that. So you can retrieve it from the Redis time series in memory again and do the inference. Maybe you need a graph data. Maybe you need to crawl some graph and retrieve this data and run it into your model all very, very fast in real time. On top of that, and that's the last point I want to cover, is that Redis is scalable. Redis by design is very, very scalable. It can automatically shard, scale out, and let you store more data and utilize more CPUs if you think that even this hundreds of thousands of operations per second that the single Redis process can do is not enough, then you can easily scale out and process more data much faster. With that, I'm going to hand it over to Ed, and he'll cover like examples. Go ahead.
Excellent. Thanks, Guy. So before we explore into more details of how those technical capabilities are used by multiple companies and that have adopted Redis for their online feature store, I want to take a step back and actually look at some of the companies, the use cases, and the common requirements and challenges that we've seen with companies like this, and some of the partnerships that Redis has forged along the way. And in particular, I want to focus in 2021, the last year. And then in my second part of the presentation, I'll focus on some of the key trends or insights that we're seeing based on what we discussed and what we saw in 2021. So if I take your mind back to late 2020, we're 6 months into the pandemic, but at that time, DoorDash publishes one of the first blog posts that cites Redis as an important part of their low latency feature serving infrastructure. And this is important. I'm going to dedicate a little bit more time to their use case later on in this presentation, but some of the challenges and key requirements that they have are as important today as they were back then. Then in April, Redis runs this annual event called RedisConf. And at that event, we positioned Redis as, we saw two key use cases or AI and ML workloads where Redis could play a fundamental role. One is Redis as an online feature store, and the second, Redis as a vector similarity or embedding store database. For the purposes of this talk, I'll just focus on the online feature store aspect. But I can take questions around our vector similarity search capabilities if that is of interest. But looking at around about that time, we started noticing a number of companies with their engineering departments publishing blog posts or presenting on YouTube and conferences. And all these companies were building their online feature store using Redis. And when you look at this, this group of companies, most of them are familiar for our US audience, but I want to call out a couple of companies that you may not be that familiar. Zomato and Swiggy. So these guys are giants of food ordering and food delivery. Swiggy operates in India and they serve 500 cities over there. And Zomato operates in 24 countries and serving more than 10,000 cities. So you can think of them as your online food order delivery giants there. So one common pattern across all of these companies is that they saw increased demand during the pandemic, right? So we all order more food, that food need to be transported, interaction, we watch more media, we increase our use of telecommunication services and found even services that we didn't know existed. So one of the less kind of obvious pattern in this group of companies is that not only they were using Redis in their online feature store, but also they were leveraging Feast, the open source project, as part of their feature store implementation. So this led Redis to collaborate, establish an ongoing collaboration with Feast. And since kind of July timeframe, we've contributed, our Redis engineering department has collaborated code into the Feast project that has improved Feast performance. Later in the year, we came across another interesting use case, and this time is another Indian company called Udaan. They are, you can think of them as a kind of B2B enabling platform. They connect millions and hundreds of millions of small businesses in India to other businesses or to end users. Not only they provide the platform and technology, but also the logistics and the capital to fund and facilitate transactions between these small medium businesses and end consumers. One of the interesting aspects when they shared their approach to feature stores is that they wanted to deploy Feast on Azure. They have a big partnership with them. In parallel, Redis was also collaborating, and we have a long-standing engineering collaboration with Microsoft. Some of our Redis Enterprise offering are actually first-party services within Microsoft, and that collaboration led culminated into Microsoft publishing how to deploy Feast on Azure. And for those of you interested, that you can check out this GitHub, super interesting approach to deploy Feast using Kubernetes on Azure machine learning, and having the host of Azure machine learning services ready to use with Feast. Then later in October, Uber, the original kind of project when it comes to feature stores, they also reported using Redis for some of the feature stores, feature sets that they store. I'll talk a little bit more in detail in the next part of the call, but this was super important for us. Kind of validated some of these capabilities. And lately, as late as last week, as I was preparing the slides for this presentation, Feast surprised us with publishing a benchmark on their online feature serving capabilities. So they compare AWS DynamoDB, GCP Cloud Data Store, and Redis open source. And I invite you to take a look at the other detailed report. So with that in mind, I wanted to focus on 3 use cases that I think are very reflective of many of the key challenges and requirements in online machine learning predictive applications. So let's start with DoorDash, because as I mentioned, they were one of the first ones to publish a blog post citing Redis. And I wanted to run you through some of the key requirements that they mentioned. So as you may expect, these guys use machine learning in many different places. One of their key use cases is what they call store ranking, which is, you can think of it as personalized consumed search result. And when you think that they have millions of consumers with millions of merchants and millions of menu items in a store, they need a low latency and persistent storage for billions of records. Not only that, when you think of the store ranking use case, they generate millions of predictions per second. So that is extremely high throughput. Also, another key requirement that they had was the ability to do real-time feature aggregation. So this is the ability to listen to a stream of events, aggregate them into feature, store them into the online store, and consistently moving that data back to offline store as needed. This is super important when it comes to online machine learning applications, that having access to that fresh stream of events and convert that into features. Another key requirement is the ability to do fast batch writes. As you are familiar, online features are typically refreshed periodically. Some of them, some of the customers that we've seen, they refresh daily, and some others even twice a day or hourly. So, but when that happens, all of those features are materialized or written to the online store in batch, and that is a process that needs to happen fast. Another important requirement for DoorDash was the flexibility of dealing with heterogeneous data types. For them, features could be stored as a string, as numeric floats, could be lists, or it could be a bunch of embeddings that already are stored as serialized as and ready for consumption for inference. And they found that flexibility in Redis. And not only that, I think in the quote that you can see on the right-hand side, you can see that they benchmark a bunch of key value store options, and they found Redis was the best. And for not only for low latency, but once they decided that, they invested additional engineering cycles to optimize their storage and serialization and compression of these features. And that led to a tripling of their cost reduction. Not only they achieved the requirements, but also they reduced their cost And high availability and scalability is super important for them too. So moving on to AT&T, as you can see, their use case is fraud detection. And this is kind of the quintessential use case in financial services and increasingly in other industries. What I found super interesting for fraud detection, and particularly the AT&T approach, is that their models use real-time features as the majority of the features. So when you look at the number of features that they have offline versus the one that they calculate online, is already a 1 to 4. And why this is important for fraud detection? Well, as you can expect, if you're just about to make a decision on a transaction, the value and the behavior that is encoded in real-time features is more important than features that don't change through time that much. If I'm about to commit fraud, probably chances are that there are a series of transactions happening at the same time that exhibit some form of unusual pattern. And the ability of monitoring real-time events, aggregate them, and turn them into features is important for fraud detection, and it was super important for AT&T. You can watch, so on the link on the right, you can watch the entire presentation covering their end-to-end machine learning platform that goes all the way from model training to deploying and serve and monitoring. But I thought what I found interesting is that the importance for online versus online features for their use case. And finally, Michelangelo and Palette Scaled. Uber Engineering recently made published a blog post and presentation of their, some of the updates that they've made to their feature store. They are kind of the original ones behind the term feature store. And over the last couple of years, they've been working on a number of optimizations. And again, some of these requirements that you see on screen are what you would expect: low latency, high throughput, stream personalization, especially when you have millions of users, restaurants, menu items similar to DoorDash, but even having models that are run specifically for a given restaurant. The amount of not just inference, but the amount of possibilities for recommenders is just huge. So Uber and some of these real-time companies share this feature of needing an infrastructure that supports the stream personalization use cases. But the next point that, and the reason that I chose to feature this use case is that they found that there wasn't a single technology that fitted all of their online requirement needs. So back in 2017, they started with Cassandra for all of their online serving needs. But as part of these optimizations, what they found was that really depending on the use case, depending on the feature set, you could serve those features very well with a simple Java cache running on a single machine. For larger data sets like restaurants that have, you could be in the tens of billions of records, they found Redis super effective for that load. So we're talking, for these tens of billions of users, we're talking hundreds of gigabytes of data. And for their larger feature sets like users, which are in the hundreds of millions and tens of terabytes of data, they stayed with Cassandra. So I guess what I'm trying to highlight here is that at this scale, there is no one single technology that can do it all at the same cost with the same, with meeting all of the requirements. Companies have that choice of building, choosing the right technology for the right feature set. It just adds obviously complexity. But companies like Uber and others at that scale will have the engineering cycles to, the engineering talent to achieve something like this. Another common requirement similar to DoorDash is efficient batch data writes. And it's about refreshing, making sure that you can execute large numbers of writes across your online feature store. And again, availability and scalability is another key requirement. So having seen these three use cases, and I'm going to go back to some of those reasons to choose Redis that Guy mentioned. And Redis is a proven technology, and for low latency and high throughput requirements. Sorry about that. For streaming support, as mentioned, this is very important in online feature stores. The ability to have data injection, aggregation, and transformation storage is super relevant. Support for multiple data structures, and as in the case of DoorDash, and high availability and scalability and cost efficiency. So these are features that you will find with Redis open source. In addition, with our commercial offering, there are a number of additional consideration and additional features that could be part of your decision making. So we support Redis on Flash. So this allowed you to offload some of those feature data into Flash as opposed to just keeping them in memory. And for the right use case, this could be, you could strike a good balance of meeting your low latency throughput and storing increasingly larger feature sets. And as Guy mentioned, one of the things that we're more proud of is the global geo distribution capabilities of Redis Enterprise. And if you're not familiar, we allow active passive deployments, which allow you to scale your reads and provide additional scalability, but also we can deploy Redis Enterprise in active configuration. So you can have your clusters for online feature serving in one region, completely in active configuration. So dual synchronization between those clusters. You have flexibility of deployments. You can find us on your database cloud provider of choice. And you can also install this on premise or having hybrid deployments, and it's fully supported by the company. So now I want to kind of close this presentation with some of the insights that we think online serving will go in 2022 and beyond. And one of our first kind of insights is that feature store vendors will target this ultra low latency kind of market and use cases. So far, we've seen examples of end user companies building their own infrastructure, and that is kind of a complex proposition. So we see feature store vendors, developing capabilities to target this ultra low latency requirements. While Feast is not a commercial offering, Feast is leading the way in defining what feature stores look like and the sort of capabilities that they should have. As I mentioned, they published a benchmark last week. I encourage you all to read it. And the TLDR is, Redis won hands down for lower latency. And it is worth mentioning that they compared our Redis open source option. They didn't compare, they didn't include our Redis Enterprise solution there. But when it came to low latency, Redis should be kind of a starting point. Another trend that we expect to see in 2022 and beyond is increased adoption in traditional mass consumer markets. Financial services and fraud detection. I mean, that's the quintessential use case in finance, but with the new world of open banking and new decentralized finance, we see a bunch of other use cases that might demand, they might require the online and real-time capabilities of an online feature store. Media advertising and e-commerce platforms with their endless uses of potential uses of recommenders is another area of growth. But one group of companies that we're starting to see and we expect demand to increase is digital native brands. So these are small companies, injected with a lot of cash and with a huge growth appetite. And not only that, they have a very deep knowledge of their customer base and behavior. In fact, they live and survive because of that capability of to provide extreme personalization and getting driving more customer loyalty, engagement, and differentiation of their service. We expect to see adoption across this segment. And in 2022 and onwards, the importance of low latency is apparent. As we explained, we cover with the case of AT&T, near real-time features is kind of the MVP signal for these models. They encode important user behavior and intent that is needed for real-time applications. And in this segment of ultra low latency, there are companies need to have this latency as the new outage mentality. When latency goes from a single digit to 50 or 70 milliseconds, as Guy was explaining at the beginning, this has a huge knock-on effect on that smooth consumer experience, a customer experience. And not only that, for companies that rely on this, it has a knock-on effect on their behavior. If they can't operate your service at the speed they require, they will go somewhere else. And another thing that is important, as I mentioned, is this geo distribution of your online features set. In this world, is not having to materialize features when you experience an outage is just not good enough. This might take hours for you to revive your online store, and it's just simply not acceptable. So you need to allow not only for scalability and high availability, but also allow for business continuity. Predictive, real-time predictive applications become part of the service that whatever service you provide. So this is important. And with that, I'll give you back some time.
Excellent stuff. Thank you all. I've been watching the presentation and thinking about different ways that I'm going to weave in some of your keywords into the song that I'm about to sing right now. I was trying to jam on some of it and see if it would work out. So that was awesome. I really appreciate that, Guy and Ed. And there are some questions I should probably, I can ask them before we jump on because it's, we've got a minute. I'll ask one about if there's a common pattern emerging, like using Redis as an online feature store with Feast, or people using just Redis standalone.
I mean, Redis is a store, it's a data store, right? So if you're trying to solve the problem of, your feature store addresses the needs of not just online feature serving, you are, obviously doing your management of features, defining your features, sharing features, all that good stuff that feature stores do. So think of Redis as the online store, the store for your online feature store, if you will.
Makes sense. All right, fellas. Thank you both for doing this. This was awesome. Now, you want to sing around or stick around and sing with me?
Let's try.
Yeah, that's ambitious. You don't know what I sound like, do you? You probably won't make me sound good. So here's how it's going to work, everybody. What we'll do is, and first, before we even do it, I'm going to highlight that we've had some great photos coming through, and I'm going to give some swag out. So stick around, and then if you want to get rid of me and you want to drop off and not hear the singing, that would be the time. But I'm going to share my screen real fast and show you all some of these photos that we've been getting, which are awesome. There's been some really cool ones. So whoever this is, that photo is hilarious. I am going to have to say, if that is you, please reach out to me and you get some swag, because if that's the face that you make before you deploy your model, oh, I love it. It's so good. So, and then whoever this is with the robots, I said you get extra credit for pets, and you brought your robot, so I'll take it. you get some swag, whoever you are. And then I saw one with a dog in here. Where is it? Where's the dog one? It was up here. Here we go. So whoever is with their dog, you also get some swag. Please reach out to me. And the other thing that I was going to mention is there was a really funny one that was happening in the Slack chat where it's like Inception that is going on. So Amulia Badal, you have a cat looking at the birds, looking at the frog, you get some swag. There we go. That is like a ton of swag that I just gave out. The way to win some more swag is by going on to Slack right now and just suggest things that I should sing about. So in case you are not on Slack, go and suggest things that I should sing about on Slack right now in the Apply Conference channel. That is what I am asking you to do. Go ahead and let's get it rolling. Let's start hearing some song suggestions. I'll start grooving. Oh, a hippo with such an inferiority complex was modeling when he realized he needed to monitor his models. Well, that hippo asked a few of his friends, what's the best way to get my model under control? I gotta know. Oh, well, the hippo got to know. Why don't data scientists know Kubernetes or much more than a little bit of SQL? Do data scientists need to know more? A little bit of all you need is a bit of Kubernetes in your life, so we can call it MLOps and be finished with that argument forever and ever and ever. Now, I want to know about feature SKUs, where they're going and what do they do. I want to talk to you about my coffee consumption. It's a little bit high. And the other thing that is so high, is the amount of ML ops communities called the same damn thing. Why is there another ML ops community? I want to know why they're all named the same damn thing. I want to know. I am looking at the landscape slide, and I can't figure out what the hell any of these tools do. I am looking at the landscape slide, and I can't figure out what any of these tools do. I went to their website. Oh my God, what the hell is happening? Everyone says the same damn thing. Let's get those models into production faster. 80% of all machine learning models never get put into production. And now I still don't know what your tool does. I'm stuck trying to figure it out. Drinking too much coffee today because my boss told me to stand up our infrastructure and the monitoring solution broke. There we go. You all were great. I really appreciate you joining in on that one. That was some funny stuff. I was expecting some good stuff, but I wasn't expecting it to be that good. And I also realized halfway through me singing this that I wanted to do some cool stuff with some effects. But next one, the May event. The May event, I promise you it will be better. So that's it. You all, I saw some great stuff coming through here from, all right. Tomas, you get some swag. Contact me. Figure out how you're going to get some of that swag. Schwiggity swag. Who else? Oh, Nikki, you were also giving me some, anybody that starts out asking you to sing about a hippo that has an inferiority complex, I like your style. All right. You get some swag, and we're going to make sure that's the best damn swag you've ever gotten in your life. So that's all we got for now. We're going to switch it up. And so these 30-minute talks are now being reduced to 10 minutes. It's what we call lightning talks. Now I am going to ask Paige, our next speaker, onto the stage. Pardis, are you around? Should I intro you in with a little bit of ukulele meditation?
I love that. Yeah.
Welcome, Pardis. It's great to have you. I am very excited to talk to you because I don't know if you, so I know we were trying to get some kind of podcast done before this event. Didn't happen. Good news is we're going to do it after this event. But our co-host Vishnu at the MLOps community, when he saw that he was invited to the chat with us, he literally wrote me and he said, "Oh my God, I love you. I cannot believe you got us a coffee session with Pardis. That's amazing." So I guess you're kind of a big deal. I had no idea.
Thank you. That's very kind.
Yeah, I'm excited to talk to you more in a longer form discussion. Everyone that wants to continue the conversation with Pardis, obviously ask questions in Slack, but be on the lookout for that podcast that we're going to do in April. I think it is April or around there. Yes. All right, Pardis. I'm going to hand it off to you. Have a great time, and I'll see you in 10 minutes.
See you. Thank you, Demetrius.
So just as a heads up, we can see it, but it's a little bit vertical, like it's on your phone or something.
Yeah, I'm trying to get the advanced. It's not showing up. Google, please.
It's all right. While you're figuring that out, let me write a song about it. Oh, Pardis is actually a big deal, and I had no idea before inviting her on the MLOps community podcast. I'm so thankful she accepted talking to us about. So we can see it fine. So you don't, oh, actually, if you, whatever you did there, it's just going, but it's all right. We can still see it. So it's fine. Yeah, if you go a little bit more like that.
We tried during the, it's not just a moment.
But it's okay. Yeah. So yeah, just actually make it wider. If you can make your window wider, that will probably do the trick. If you can make your window wider, Yes, there's full screen. There we go. Whoa,
yeah,
oh,
so-
go back.
Sorry, because I want to see the speaker notes.
Oh, yeah. Okay, this is fine though.
Yeah, so I'm not sure
It's not a
why
big deal.
this.
Don't worry. And no pressure. We can always like cut into my blabbing after this. So feel free to take up the 10 minutes and I'll make the next one really, really fast. So yeah, I'll hand it over to you. Talk to you soon.
Talk to you soon. Thanks. Hi, everyone. Sorry about the technical difficulties, but the slides aren't that important. I'm mostly just talking about everything. So it's just an aid. I'm Pardis Nurzad. I've built and managed data teams. I previously worked in healthcare at Carbon Health, social networks at Twitter, payments at Paytm, and e-commerce at a startup that has since been acquired, RubaCloud. Today, I want to talk about some of mine and others' experiences in evaluating ML platforms, both those which cover the end-to-end and those which cover distinct parts of the ML pipeline. Just recently, I spoke with around 20 ML platform companies and 10 other data platform companies to understand the challenges they face in ensuring client success during the evaluation phase. In particular, I was interested to understand the challenges at the very first step in the evaluation process, which is that of data collection and transfer. So I want to talk about how platform companies address some of the existing challenges, some of the needs that remain unmet, and finally, some of the properties of a potential solution. As we go through these topics, it might help you recall some of your experiences that you might already have. You might have had in, any ideal solution or ideal features that you have in mind. It would be great to connect and continue the conversation beyond today's talk. When it comes to evaluating platforms or any piece of software, one approach is to allow customers to install on-premise, right? So to avoid transfer altogether. This works particularly well for open source solutions and also proprietary solutions, which can be packaged and installed on-prem. Of course, the drawback to this approach is that you need to ensure that your customers are savvy, such that they use the platform as is intended to its full potential to ensure a fair and correct assessment of the capabilities and features of the platform. This is one of the reasons why, as you know, many software companies skip this approach and move directly to a hosted cloud solution. This way, they can more efficiently manage versioning, bugs, customer service. Another reason has to do with compute and GPU resources. Platform companies sometimes need to tune and manage the cloud services in a way to manage costs, performance. Sometimes they want to move data to where GPU costs are affordable. All of this is not something that can be ensured with an on-prem solution. Now, the good news is that many platform companies offer cloud-native solutions spanning multiple cloud providers. And so once the customer signs an agreement, no transfer of data would be necessary. However, this is certainly not the case for all platforms. And therefore, sometimes data transfer is inevitable. The issue is that even before getting to that final step, as companies evaluate the platform of choice, they are required to transfer data to the platform such that the results can closely mirror the outputs as they would in a real world setting. So let's talk about the status quo in data transfer and some of the workflows used for transferring data today. Now, one of the most popular methods is to set up an SFTP server, download the data from the warehouse into a CSV, upload the data to the SFTP server. The receiver then downloads the data, then uploads it to their warehouse using some non-trivial tool. Another approach would be to replace the SFTP server with a cloud storage bucket. In both cases, data needs to leave the cloud, get stored as a CSV where important type information may be lost. temporarily stored on some computer, then with the help of additional tooling uploaded to the lake or warehouse at the destination. Obviously, this is not fun. There are a variety of tools and services for cloud-to-cloud transfer, direct transfer, but the market is very fragmented, and a solution would be specific to a particular choice of cloud. This makes the task not something either side really wants to take on. Additionally, as these pipelines become more complex, they leave the scope of the data team, and the task falls on DevOps or engineering teams to facilitate the transfer. This is not ideal, as the platform companies want to interact directly with the teams which will become the users of the platform as they iterate on the required data to be transferred with the team. And so want to work with a team that has the domain knowledge and the use cases and actually wants to make the final decision. Also, managing security and staying compliant is not easy and sometimes close to impossible. However, even during the evaluation phase, customers are required to stay compliant with HIPAA, GDPR, CCPA, and other legislation depending on the type of data they manage. Without the right tech, it's difficult to remain compliant. Local machines are not the best place to store data, even temporarily, before uploading to an SFTP server. Sometimes customers mistakenly send data containing PII without the right contract in place. That's personally identifiable information. This means that their teams would now be responsible to scrub the data. With the current approach to data sharing and transfer, it is difficult for either side to send requirements or validate the data in flight. Don't send PII, for example. Maintain the schema. Ensure data is complete. For example, for a forecasting task, ensure data contains entries for all days of the week or all seasons. For the fraud detection task, ensure that the main types of fraud are captured. And this is not all. When customers are evaluating multiple different platforms at different times, each gets a slightly different version of the data since different people could have been responsible for the transfer. It's hard to keep track of source of truth, which causes issues in the fairness of the evaluation. It also makes it difficult to handle audits. Which company was sent which data? So what do we look in a solution? There has to be a better way, and there should be. So we want a stack agnostic solution that could work for any two peers, so platforms and their customers can focus on the task at hand instead of the nuances of cloud storage infrastructure. A platform's cloud strategy should not be the reason why customers are not signing up to see a POC, why they're evaluating fewer platforms, why they can't find the best solution for their particular needs. We'd like to be able to manage one source of truth that we share with all platforms while we're evaluating. And we want it to come at not much of an additional time investment per platform for the customer. Managing privacy and security and staying compliant is easy when you have the right tools that manage the transfer of data. Handling permissions and processes, handling masking, hashing, encryption as needed allows companies to start sharing data more quickly and sometimes without having to commit to complex agreements upfront. This takes us to the important topic of data validation. As we previously spoke about, both sides should be able to run tests to validate the data in flight. The customer needs to ensure they're not mistakenly sending private fields, for example. They need certain automated tests in alignment with the various types of legislation with which they need to comply. The platform company may have certain requirements that they would like the data to meet, so they too can create tests. Unlike traditional software applications, ML systems depend on a lot of data to evaluate, and that's really key here. In every ML project, a lot of time is spent bringing data to where it needs to be. We want to move from manual script-driven transfer to something easier and more secure. So we're in the discovery phase. We want to work with you to bring this to life. Let's connect via Slack, on Twitter, LinkedIn, email. Thank you for listening. Thanks to Kevin, people at Applied Tecton for having me here today. Thanks to Dimitrios for the extra time.
No worries. So it looks like somebody shut off my video and maybe they're trying to cancel me. Maybe after that session, they said, hey, you need to get out of here, the music session. But thank you, parties. That was really cool. Hope I didn't throw you on tilt trying to tell you to change the size of the slides. They were perfect size. And for everyone that wants to get more questions from parties, get in Slack and we will, she'll be answering stuff there for the next little bit. And then also stay tuned because we're going to do some kind of podcast coming up. I'm excited to talk to you about all this and more when we chat. So we're going to keep cruising. We're staying at it. More lightning talks. And this time we had one side of the Tecton sandwich, which was the CEO, Mike. And now we get the other side. We've got Kevin coming up. Oh, look at paging Kevin to the stage.
What's happening?
How you doing?
Good. How are you?
So I'm really good. So I just want to remind you of something you told me the first time I interviewed you for the MLOps community. I asked you, what exactly should I need to know about Germans now that I live here in Germany? You said something like, oh, we're nice people once we warm up to you.
No,
I understand why you left the country. And what, you live in Hawaii now or something?
Oh, I'm in New York.
It's cold, man. It's not the people that are cold. There are nice Germans out there, don't get me wrong, but this place is freezing. It's like snowing outside right now. But luckily I'm getting into my ice bath and we don't have much time. So I'm going to let you give it a go. I know you got all kinds of cool stuff to talk about when you were building Tecton, Feast, and Michelangelo. And I'll let you just get right at it.
All right, let's do it. Well, nice to meet you, everyone. I'm Kevin, co-founder and CTO here at Tecton. And in this chat, I'm going to shed some thoughts on how to think about picking the right online store for your feature store or for your ML platform. Quick recap, what's a feature store? I'm sure most of you know this already, but it is, at the end of the day, the interface between your data and your models. It serves real-time features to your models that are running in productions, that are making predictions, and then it also serves historical features to your model training. The way it does that is that a feature store typically doesn't just implement its own database. Instead, it abstracts access to an offline store and to an online store, depending on the usage. And in contrast to an offline store, the online store is used to serve features for online predictions. And it typically only serves the most recent feature value for a given entity. Also, typically, you only care about the feature value for one entity or for a handful of entities. Typically, the load can be quite high. It can literally get into the hundreds of thousands or millions of queries per second. The feature vector is quite small, a couple bytes, kilobytes in most use cases. And then finally, latency matters a lot for the online store. And basically, the offline store is the exact inverse because it powers your training that has completely different characteristics. But let's focus on the online store, and which one should you pick? Well, if you sample the universe of a couple of ML platforms and feature stores out there, you see a variety of different choices the company have made. One thing that stands out here is that a key value store is typically quite popular as a category of online store. And the most prominent and popular choices are typically that we see Cassandra, which we used at Uber, Redis, or DynamoDB. But as you try to figure out, hey, which one should I use for my own platform under the hood if I have to build my own? Here are a couple of considerations that I think are really important to keep in mind. First one is, what does your team already know? What are they familiar with? What are the online stores you already have in your stack? If you bring something else in, of course, you're signing yourself up for a bunch of unknown unknowns, a potentially steep learning curve. Best avoid it if you can and already have a good system in place that you like. Second, figure out whether you want to invest the time and the resources to manage a store on your own, or whether you really prefer the luxury of having somebody else manage a store for you. In most cases, I would recommend going with a managed service so you don't have to waste any time and resources on having to manage your own. And of all the stores out there, we found DynamoDB to be pretty good. At Uber, we had an internal team that was fully dedicated to managing Cassandra clusters for the different consuming application teams, including the Michelangelo platform team. Next, of course, you want to look at, well, what's the latency requirement of your end-to-end ML prediction pipeline? And what's the budget you have available to fetch the features from your online store? And not just the median, but also what tail latencies can your use case stomach without deteriorating? Are you okay with up to 100 milliseconds? Or do you really need tens of milliseconds, or maybe even less than that? Or does it not really matter whether you're at 100 milliseconds, 500, or even maybe a full second? If tail latencies really matter to you, we found that Redis outperformed in our benchmarks Dynamo in pretty much all cases. Next, of course, the read and the write load is super important to keep an eye on too, both today and what you expect to hit in the future. Do you have a use case that's extremely write heavy or extremely read heavy? Like for instance, maybe you have a streaming feature that just hammers on the online store, which is something that you'll have to keep in mind as you look at the different options, and especially their cost efficiency, which we'll look at in the next slide. Also, think about, well, do you only need to fetch individual rows and look those up for individual entities? Or do you need to submit more complex queries? Also, are you okay with eventual consistency, or do you require the typical ACID properties? For most use cases that we've seen, key value stores are the best option, wherever you require only individual row lookups and you're fine with eventual consistency, because they just perform in most cases significantly better than your typical relational database, because they don't have the transaction schema, the locking overhead that you would find with those. And then finally, cost efficiency, extremely important, because the pricing model of the different databases is typically can be super different. And the impact on the final cost of your system can literally be orders of magnitude different. Some stores, like DynamoDB, charges by writes and reads, where writes are significantly more expensive than the reads. Other databases only charge by the number of nodes that you have and their provisioning. And depending on your use case, one may be significantly cheaper than the other. And in our benchmarks, for instance, if you have a really write-heavy workload and it's pretty steady, Redis beats Dynamo in pretty much all cases. But if you have super sparse traffic and it's not super predictable and the load is fairly low, DynamoDB can be cheaper. And at Feast and at Tecton, we've run a few benchmarks. You can find more details on those on our website. And specifically what we did here was one high-scale benchmark where we ran 20,000 feature requests per second, each one of which fanned out to 10 different tables. So it hits the database with 200,000 requests per second. And I'll show you now what the results here look like between Redis and Dynamo. But first, disclaimer, this isn't a TPC approved benchmark. So this is just one representative benchmark of what we see our customers typically do with our feature stores. For this high-scale use case, we found that Redis did outperform Dynamo, specifically on the tail latency. It performed really, really well. And the cost for this high-scale, not super varied use case is significantly cheaper and different to Dynamo, which is why at the end of the day, we decided to integrate Tecton and Feast with both Dynamo and Redis, so customers can really choose based on their use case and their feature, which one they want to use under the hood. Now, finally, I want to leave you with some quick rules of thumb as well. Typically, I'd recommend if you have a really high scale use case and tail latencies really matter, Redis is a pretty safe choice. If your load is super sparse and you care a lot about the management convenience, DynamoDB is a pretty good option. But if you care a lot about super strong consistency and complex search queries for like candidate generation use cases and stuff like that, Aurora is a pretty good option as well. But at the end, not all ML use cases are created equal, and it really depends on what you have. So ideally, you can federate out to not just one, but multiple stores. And with that, I'm happy to take any questions.
What's TPC stand for?
Oh, I don't even know the exact behind the scenes.
What does it mean though? Like it's just like actually approved by a third party?
Like a central non-for-profit organization that comes up with standardized benchmarks. The database is typically used to compare which one's more performant than the other.
Oh, somebody just put in the chat, transaction processing. All right, nice. And one more before we jump, and everyone that has questions, feel free to ask them in Slack. Feel free to jump over there in Slack. What I'm wondering is, do you see a lot of use cases where people are using multiple stores? Like they have multiple use cases and they're like, oh, well, because Redis is better performant in this use case, I'm going to use it. And then Aurora, I need for those bulletproof use cases.
Typically, the companies we've spoken to right now, they typically have one store because that's the easiest way to get started with something. But we see now with our own customers, for instance, where we started with Dynamo, and for some high scale use cases, it's just cost prohibitive, which was why we're now giving them the option to, for that use case only, use Redis. But if you're just getting started and have a first ML platform or feature store, I probably wouldn't immediately implement federation.
Excellent. All right, man. There's a few good questions coming through in the chat and on Slack. So I'll let you get over there and answer them as we keep this train moving. We have got another lightning talk, this time from the partner sales engineer for AI and ML, Miles Adkins, paging Miles to the stage. Where you at? Hey, what's up, man?
Oh.
You good?
Hey, how's it going?
I'm good, man. I'm very good. So I hear you come to talk to us about Snowflake.
Yeah, 100%. It's a blizzard out there.
That's the truth. I live in Germany. So let's talk, man. I'm going to hand it off to you just because we're low on time and we'll keep it going.
Sure thing. Okay, so yeah, this will be a talk about building feature stores on Snowflake. So many of you know Snowflake has been around for coming up on a decade now, and we started off as just this other an alternative data warehouse, right, in the field of many different options. What separates us from the competition today is we are now the data cloud. And so because we're the only third true multi-tenant SaaS company, this allows us to really go from being a data warehouse to a data cloud, meaning you can now integrate with your first party, your normal organization data, but in addition to start working with second party, your partners, suppliers, vendors, and then even third party through a data marketplace. And I'll get to a second on why this is relevant. And if you just think about it, if you have like a data cloud plus a feature store, could we have like an actual feature cloud where, different companies and whatnot are just sharing their features as well. And so that's pretty awesome. When it comes to being a data cloud, you're really not going to go far if, you don't have the compute power to back up your name. And so Snowflake as well is this highly scalable compute place where you can program in your language of choice. SQL, of course, is kind of the standard today for your traditional warehouse, but through our Snowpark program, you can now start programming in Java and Scala, and soon to be Python as well. So it doesn't matter if you're a SQL guy, a data scientist, an analyst, we're working on supporting a programming language for you. And of course, giving you kind of that fastest processing engine with no operational overhead while we're at it. And so how does this fit into kind of feature stores? How does Snowflake fit? Where we see ourselves today is really checking off a lot of the boxes of what an offline feature store should provide for you. And in addition to that, I think bringing our unique data sharing capabilities, as well as our unique ability to store kind of 3 types of data as well, is going to expand, what the true requirements for an offline store are. And so, of course, today we kind of see this in 3 different angles. One, by feature type. Of course, we can do batch features pretty well, along with batch aggregate features. Through our new UDF capability, you can now start computing real-time features as well. So if, for example, I'm going to apply for a credit card, along with that form comes my IP address, I can quickly compute, because I have access to all these additional tables within my Snowflake account. I can say, hey, look, based on this IP address, I can now compute geolocation. Oh, wait a minute, this person is in a different place where they say they are. Maybe we have some fraud there. That would be a real-time feature. On the second dimension, as I alluded to, we have support for all 3 types of data. So whether you have your normal structured numeric categoricals, those will all fit in fine like any data warehouse would for you. But when it comes to semi-structured and unstructured data, we can now allow you to start registering features on things like images, video files, JSON blobs, Parquet, really enabling you to do a lot more with some of these more advanced neural network type modeling approaches that are out there and available to solve a variety of different problems. And then, of course, the last thing, and I think this is the most differentiating for Snowflake, is our data collaboration. So how can you start building features on not just your first party data, but talking with your supply chain, talking with your partners, vendors, et cetera, to share data amongst private data exchanges to better make the entire system go, whatever that means to your organization. And of course, this third-party data marketplace where I can now start pulling in weather data, IP to geolocation data, aggregate retail sentiments about shopping trends, media, et cetera. And that is all a first-party object to Snowflake. And of course, will be a first-party object to your Snowflake store as well. And so with that, happy to announce that we are now available on Feast as a offline store as well. I guess I'll pat myself on the back. I was the main code contributor, but hoping that you guys are able to get a flavor of everything I just mentioned in terms of kind of what makes Snowflake level up the game for being an offline store. And so with that, thank you, and I'll take any questions.
All right, sweet. And cool. That was perfect. And while we're waiting for some questions to come through, I like that you pat yourself on the back for that one. That was good. Now, what were some things that you ran into? Like, what was a challenge as you were trying to put that together?
Yeah, I would say the main challenge is I'm not really a software engineer was kind of the hard part. I mean, we've heard from just our customer base that, hey, we want to get started with Snowflake and feature stores. What do you have for us? And at the time it was, well, we don't really have anything for you at all. And so I kind of just picked up Feast, on the weekends and the nights. And, shout out to some of the Tecton folks to kind of hold my hand along the way. But yeah, super excited and, just trying to up the game for what a feature store should be from the infrastructure perspective.
That's awesome. And last one before I start talking about some of these results that we have from the poll. How does Snowflake plan to support unstructured data? Would I be able to throw images, audio into Snowflake at some point?
Yeah, you can do that today, actually. The way that works is we're just built on top of good old blob storage and compute boxes. So you can throw that all in there. We'll create basically a metadata table for you. And then you can start pulling in your unstructured data into our compute to do things like named entity recognition, object detection, all through our UDF capability.
Awesome, man. Sweet. Well, we're going to keep cruising. That was very cool. I appreciate it, Miles. And for those that are interested, Miles and I had a great conversation with Willem, the creator of Feast, for the Feast podcast that we're doing. I can share a link to that when it's out. It should be out probably in the next couple weeks, I hope. And so we talked all about Snowflake and Feast and feature stores and machine learning with Snowflake, because I know that's a hot topic, big on a lot of people's minds. Now, I want to share my screen real fast because we've got some preliminary results of the community poll. So if you're asking yourself right now, what is the community poll? We'll leave a link to it in the chat, in Slack, everywhere. It's not too late to tell us how many models are you running in prod. It looks like a fair few, more than half of us are running 1 to 10. That's good. That's better than none, I guess. So 12% have got none. And look at that, 9%, almost 10% have over 100. That's pretty cool. That's really cool to see. I mean, if we take the 9 and 16%, that's a good chunk from 30 to over 100. Well done. We've got some sophisticated watchers out there. Kubernetes, agree, neutral. Wow, that's split down the middle. Wow. All right. So how long does it typically take you to build a new model and deploy it into production? This is where some people are going to weep and some people are going to beat their chests. 2 weeks, 1 month, 2 weeks, 16%, 1 month, 20%. So that's a good chunk. That 1 month time period is not that long, to be honest. Of course, it could always be shorter. 16% is 1 year or more. Whew. So I'd love to hear more about why it takes over a year. That's some interesting stuff for me. So if somebody is taking over a year to put their model into production, I want to talk to you on the MLOps community podcast and just see what you're doing, because I'm sure there's probably a specific use case and there's a reason for that. Or maybe you're really trying to make that better. Anyway, last one. Does your team have a dedicated ML engineer? 62% said yes. That's cool. That's up since the last time that we asked. That's way up. All right. And then 37 say no. So sorry, DevOps folks who get thrown, they get thrown stuff over the fence. All right. And then last stuff, which ML ops tools are most critical in your team's success? Model serving, model training is up here at 20%. Feature stores, 45. Oh no, sorry. So I was reading this wrong. 20 people said that, 65%. 14 people said feature stores, observability, model serving. That's interesting because I've seen a lot about model serving in the MLOps community. Then experiment tracking. You would never think that with the amount of attention that weights and biases gets, and ML flow. Anyway, what type of data processing do your features require? Batch, streaming, real-time, NA. Batch. Looks like we're all on batch. Contrary to what Chip says, ML is not going real-time just yet. But maybe she knows something we don't. All right, so we're going to keep cruising. We've got our next guest coming up, who is, I believe, Felix. You've come on the MLOps community podcast meetup some time ago, and you talked about the Feast. Now you're going to dive deeper in managing the data infrastructure with Feast. Felix, I'm going to hand it off to you because I blabbed a lot on those community polls. Please, if you have not filled out the community poll, go and do it. We're giving away a bunch of swag. And for those who are talking to us about their model gone rogue stories, we have special awards that we're going to be giving out to you at the end. So tell us about a model gone rogue story. We're also going to just give awards to a lot of people depending on what they've been doing, if they've been helping out or if they've asked great questions, or actually some of the presenters. We're going to give like best presenter award or whatever. I'll just make something up. So Felix, it's all on you, man. Take it over from here.
All right, thanks very much for that introduction. Hi, everyone. My name is Felix. I'm a software engineer at Tecton, and today I will be talking to you about managing your data infrastructure with Feast. So first of all, what is Feast? Feast is an open source feature store. We entered the Linux Foundation for AI in September of 2020, and we've really seen a tremendous amount of growth since then. We're now an active community with 3,000 plus members on Slack and bi-weekly community calls, which I would encourage you to stop by it if you have the time. And we've also seen a lot of contributions from a wide range of tech companies such as Twitter, Shopify, Robinhood, Salesforce, Gojek, IBM, and of course Tecton as well. And you can see a bunch of other logos down below of teams that are either running or contributing to Feast. So now let's take a quick look at the architecture of Feast. We really have a strong focus on the cloud native and the serverless experience. So Feast works extremely well with data warehouses such as BigQuery, Redshift, and of course Snowflake, as Miles just talked about in the previous lightning talk. We also aim to be extremely modular and extensible, and we have connectors to AWS, GCP, Azure, Snowflake, Redis, Hive, and a few more that are on the way. And I really want to emphasize the fact here that Feast is extremely extensible. And this is because we have a few core abstractions, such as an offline store and an online store, which make it really easy for folks to just plug into and write their own connectors. And I think the Snowflake example is actually a great example right there, where because we expose these offline store and online store abstractions, Miles was really easily able to just write this plugin and then merge it into the main Feast repo. And so in general, we found that these abstractions make it very easy for contributors to come by, run Feast with whatever custom stack they have, and also contribute whatever connectors they write back to the community and merge that into our main repo. So we've really seen a lot of success there. And finally, we don't need to dive into too much detail, I think, since we've talked a lot about feature stores today. But as you can see from the center of this diagram, Feast has all the standard functionality of a feature store. We store your features for you. We transform and execute transformations. We serve those features as well. We recently added data quality monitoring capabilities. So this allows you to examine your training data sets, your data during serving time, and also check for training serving skew to make sure your models aren't going to go haywire due to some training serving skew. And of course, Feast also allows you to register and discover your features in some central repository, which makes collaboration super easy for data scientists. So all the standard functionality for a feature store. Diving a little more deeply into the data infrastructure, and I'm sure most of you folks are very familiar with this, there's really two core flows when it comes to Feast and feature stores in general. The first is this offline flow, which is represented by the bottom half of this diagram, where a user, typically a data scientist, will use Feast to query the offline store, and that will yield some kind of data frame, which they'll plug into some training algorithm, and that will yield some model, which will then end up being put into some application in production. And this is typically done in a notebook, probably. The second flow is the online flow, where users will first materialize features from the offline store into some kind of low latency online store, and then they'll retrieve features from the online store, serve those features to the model in production, which will then power some kind of prediction. And so zooming even a little bit more into this online serving flow, as I was just talking about, Feast will materialize those features for you from the offline store. As I mentioned, that's typically BigQuery, Redshift, Snowflake, into an online store, which we most commonly see Redis and also DynamoDB and Datastore being used. In terms of how features are actually being retrieved from the online store, we have a whole bunch of different options. We have the Python SDK, which you can use, a Python server, as well as a Java server for folks who are a lot more latency sensitive. We also have published a bunch of benchmarks around those servers. So if you're curious about what kind of latency requirements we meet, you can definitely go check out that blog post, which I can link to later on. And finally, if you don't really want to run or maintain your own servers, Feast also has this option to set up an AWS Lambda. And so if you just plug a few lines of configuration into Feast, we will just spin up that AWS Lambda for you. And it should be super easy for you to get up and running with the feature store and serving features to models in production in just a few minutes. And we'll actually go into example workflow in just a couple moments, which talks about the AWS Lambda in more detail. So moving on to the next section, let's talk about how Feast actually manages your data infrastructure and then walk through a quick example to show you in more detail. So there's two really central things that Feast needs. The first is some declarative definitions of your features and transformations, data sources, et cetera. We refer to that as a feature repository. And the second is a central configuration file, which we've named by default featurestore.yaml. And of course, it's a YAML configuration file. The figure you see on the left here is basically illustrating an example featurestore.yaml file. So why don't we take a look at this and see what's going on. So you see a project, which is a Feast project, which is basically scoping all the feature definitions to allow data scientists to collaborate within that project. We have a registry, which is what stores all those feature definitions and associated metadata. So you can see that's basically just a file on S3. And in the third line, you see that we've denoted we're using AWS as a provider. And the provider is really just an abstraction which wraps the offline store, the online store. And so if you choose AWS as a provider, that means by default, we'll use Redshift as your offline store and DynamoDB as your online store. And so that's why you see, this US West 2 as the region for online store. Of course, you have to specify that for DynamoDB. And then you also have to specify these things like your cluster ID, your user, your database, et cetera, for Redshift. And finally, in the last three lines, you'll see we have this feature server area, and we've set enable to be true. And what this means is you're telling Feast, look, I would like Feast to just spin up this AWS Lambda, launch that for me, and then you should be really easily able to query features from that. And so basically the way Feast works is, in terms of managing your data infrastructure, is you plug in this featurestore.yaml, your feature definitions, and then once you run Feast apply, the command, which I'll talk about in the next slide, Feast ends up configuring this infrastructure for you, which in this case is two different things. One is DynamoDB, and the second is AWS Lambda. In terms of what tables are actually getting constructed in DynamoDB, that depends on the actual feature definitions that you make, but that's not a thing you have to think about. Feast will basically configure all of those under the hood so that we can serve the features at low latency, and you don't really have to worry about that. So in terms of launching your infrastructure, there's two main commands to be concerned about. The first is Feast plan, and the second is Feast apply. Of course, these are basically analogous to what you would find in Terraform. Plan will show you a preview of the changes to be made, and apply will actually apply those changes. And so in this case, you can see the output of a Feast apply command. Maybe what you did was you defined an entity in a feature view. And so you see that Feast is telling you we created an entity in a feature view. And then because you created that feature view, Feast will also create a DynamoDB table that corresponds to that feature view, which you can see right there as well. So now we've covered, what it might look like to launch some data infrastructure. Let's go through an example really quickly. So if you're a data scientist, you want to use Feast, probably the first thing you might do is define some data sources. And so you see here, there's a Redshift source for your driver statistics, say, and also another Redshift source for some user statistics. You can see that we've pointed those two sources at respective tables called driver hourly stats and user stats. And you also define two entities called a driver and a user. The image on the left is a schema which might represent the data in, say, your driver hourly stats table. And you can see here, there's 5 columns. You have an event timestamp column, which is, of course, a timestamp indicating, when this feature was recorded, a driver ID column indicating what driver this row refers to, and then 3 actual feature values, a conversion rate, an accuracy rate, and some average daily trips. So now that you've defined these data sources and these entities, your next step is probably going to be to define some feature views, which package these features together. So if you take a look at the feature view on the left, you'll see it's given a name, the entity, which refers to the driver. You define the 3 features, which are precisely what we just covered. And then finally, you point your batch data source at the table, the Redshift source we just defined. And so from there, you're basically good to go. You can plug in the featurestore.yaml file from a few slides ago. And just to go back, that looks like this. You basically just configure stuff with AWS. And then once you run Feast apply, we tell you we created 2 entities, created 2 feature views, created 2 DynamoDB tables, and also launched that AWS Lambda feature server for you. And so at that point, you're basically good to go. So that, in a nutshell, is how Feast might manage your data infrastructure. And finally, really briefly, I just wanted to touch on how Feast might fit into a CI/CD context. So today, most ML teams will version their features with Git. And so what will happen is a data scientist will create a PR, And then once that PR is merged in, CI/CD will typically run feast apply, which will construct that feature in Feast as well as update any infrastructure that's necessary. And another thing we've recently started recommending to users is you can actually make this process even more reliable by running Feast plan on every PR. And so you can have some GitHub Actions bot, some workflow, which every single time a PR is run, it'll automatically run a Feast plan. It'll show you the expected changes to be made. So you can see here, if you add a feature view, the expected changes are going to be a new feature view and a new DynamoDB table. And that way it's really clear to both the data scientist and say the ML engineer who's reviewing this PR exactly what infrastructure changes are going to take place. And so this makes your CI/CD a whole lot more reliable. It should eliminate any kind of weird flukes where you accidentally delete, say, a DynamoDB table that's serving some model in production. And yeah, that's how Feast and CI/CD might work together. So that's it. That's the end of my talk. And thank you very much for listening.
Awesome, man. So there's a few questions coming through in the chat. I am going to ask that you ask these questions in the Slack channel, but I'll ask one that I saw coming through in Zoom because it's a really good one for you, Felix. Does the online store only get updated via materializations from the offline store, or can updates be streamed from other upstream systems?
That is a great question. And in fact, that's actually one of the things that our team is really starting to focus on. We've had a lot of requests for basically being able to write directly from streams and ingest into the online store. And this is currently being worked on. We support it for Redis as an online store right now, but we're planning to support it for all the other online stores coming soon. So yeah, it's definitely one of the top priorities for our team right now.
Amazing. All right. Now we've got another little break before we totally cruise forward, except luckily for me, I haven't been on time at all. I am the worst timekeeper ever. And so that break kind of got eaten up just a little bit. Luckily, I don't have to answer to anyone on the timing. So that being said, I'm going to say like 2 words and then we're going to just keep rolling. The 2 words that I am going to say is I would like everyone at the end of this to vote because we're giving away awards to the different speakers. So I want all y'all to vote on what your favorite long talk was, aka 30-minute talk, and what your favorite lightning talk was. Don't vote yet though, because there are still a few aces in the hole. I know Ben Wilson and Joe Reese are coming up, and I would not discard them on the lightning talks. But for now, we're going to just keep moving. So we have Svetlana to the stage. Svetlana, you around? Can I page you to get ready? Come on. There you are. All right.
Everyone.
What's going on?
Not much. Just great to be here.
Yeah, it's very cool to have you. So I know you're going to talk to us right now about all kinds of cool stuff. You're a staff ML engineer in the ML platform organization and a tech lead in the feature management team at Twitter for the feature store, which is really cool. I can only imagine how many people have questions about how Twitter does their feature store. So I'm just going to let you take over and then I'll be right back in 10 minutes.
Cool. Thanks for the intro. I hope that this talk is going to answer some of these questions. All right. Cool. So in this talk, I will share Twitter's story in building feature stores. I will assume that the audience here is on some level familiar with feature stores and the motivation behind them, so I will not focus on that. So the need for something to manage ML features came early at Twitter, but attempts up to like 3-4 years ago were driven primarily by product ML teams, and none of them quite stuck. We identified several main reasons for this, both technical and organizational. So for example, one solution using a single proxy service ran into operational issues for the owning team and latency costs incurred by the service in the middle. In another case, there was fragmented feature data and transformations ownership, which meant poor maintenance of features and extra overhead for the team owning the system. And the owning team being a product team versus a platform team meant weak platform ownership. So there were little incentives in operating the infrastructure for other teams. This, as well as the increased investment in a global ML platform at Twitter, led to a small but dedicated team to begin building a global feature store solution. And what we currently refer to as Feature Store 1.0 was built as a virtual feature store. The distinction between virtual and feature stores, I think, is now well known in the space. Virtual stores essentially represent a framework for registering and accessing features in a uniform way from already existing data. And physical stores, on the other hand, incorporate physical components like pipelines for data ingestion and aggregation, the actual data storage in data lakes and in real-time serving solutions and services for access to the features and so on. All of this managed by the team that owns the feature store. So why did we start with a virtual feature store? So virtual stores are quicker to build and to enable for multiple customers with limited resources for operational overhead. Plus, Twitter already had a huge number of data sources available both in data lakes and in real-time serving solutions, and many of them already used as ML data. The physical and operational cost of extra duplication was high, especially given that our vision was to have all features for all teams be in the feature store. Twitter also had existing frameworks for aggregating batch and real-time data, and so making that data easily accessible and shareable was what was needed. And the North Star was, when we started, was sharing. So we wanted to quickly facilitate the reuse of features, making features from large teams with a lot of resources available to smaller teams that were just starting with ML. So in its core, Feature Store 1.0 is a JVM-based library for registering reusable extraction and transformation logic, client code for accessing the underlying data, applying these transformations on online and offline settings in a consistent way. We are particularly proud of the easy-to-use APIs. Our domain-specific language for registering features allowed for almost all types of transformations that our customers came up with. For example, feature crosses, like a feature computed from some user data and some tweet data on the fly, or feature aggregations for getting the, say, average age of all mentioned users in a tweet, for which we will automatically fetch the age for all user identifiers in the request and average it. We refer to this as entity management. So in addition to managing the raw feature and indexes, we also manage how it all comes together for a given model. The guiding principle was that after some initial setup, adding a new feature is a one-line effort in some configuration file, for example. This solution is still a GA system at Twitter with pretty wide adoption, both in the number of teams using it and in the features registered. And here I want to mention that a couple of years ago, we did our first evaluation of Feast as something we could potentially integrate with. However, the infancy of Feast as open source software at the time and the big difference in the tech stack and in the approach led us to pass at the time. We ran into quite a few challenges with our first generation feature store. Because performance was not our North Star, and our online client was kind of trying to do it all, we ran into a lot of latency related challenges with some very high throughput, low latency use cases. For example, some of the advertising related models or the scoring of thousands of tweet candidates for the Twitter home feed of tweets. Also, while our offline access API allowed for time consistent joins, it was based on scouting and Hadoop, not very fast, unfortunately. And for many customers, it was still easier to fetch feature data online, like log it or scribe it for a long period of time, sometimes months, and then use that as their training data. And there was still a large operational burden on feature producers who owned offline and online storage of the data. Last year, the ML platform began moving towards GCP in a hybrid cloud strategy. So the new tech stack and the new customer challenges around getting data to and from the cloud required a new approach. for the next generation feature management, we had a few added goals: to take on more of the data operational burden from customers, fast online performance, and to speed up offline experimentation with features were some of them. In spring last year, we did another evaluation of Feast. And at this point, our stack seemed well aligned. So Feast's plug-in play model provided a lot of flexibility, and we were eager to integrate more open source software in the ML platform in general. So we decided to adopt Feast as the framework to bring it all together. And here is the bird's eye view of our system. It consists of various offline and online storage infrastructure, all tied together through Feast. One key difference from our previous iteration is that as much as possible, feature transformations are pre-materialized in storage rather than performed on the fly. We have done quite a few contributions to enable Feast for our use cases and have taken advantage of the flexible model to enable our own online storage. So what's next for our next-gen feature store? Well, we are excited about continuing working with the Feast community and push the limits of Feast with more Twitter-heavy use cases. We are building a highly performant direct fetching client, but we will also be working towards integrating feature hydration and model serving in a single managed service as an option for our customers. And while streaming and on-demand transformation existed in our old stack to some degree, we still need to bring those to our next generation platform and are looking forward to making use of the functionality that the Feast community has been adding in this space and contributing to it. Data quality monitoring and better linking of model and feature metadata is also something on our list. So here's some lessons. We had more than what I can fit on the slide, but some of my favorites here. Probably geared more towards companies with multiple ML teams and considering having a global feature store. As hard as it is to build a global feature store, it results in an active feature marketplace and community. And we really enjoyed watching that grow. So feature stores can target many different problems in feature management, in the feature management space, like discoverability or feature generation, aggregation, offline experimentation, versioning, embedding support, to name a few. And they can look very different depending on that. So can be good at one thing and not at another. So be sure to understand what aspect of feature management matters to you the most and pick a good North Star. We got a bit burned with chasing some very specific feature transformation use cases, and we intend to not do this with our second generation store. Another one was around guaranteeing consistent runtime performance, which we thought impossible that for every imaginable access pattern. So investing early in benchmarking and also setting the expectations with customers can help with that. All right, this was quick and high level overview of our story, but if I have piqued your interest, feel free to reach out to us in the Feast Tecton Slack channel.
Amazing. Oh, I have so many questions that I want to ask you, but I also want to keep going. There's so much cool stuff. I'm going to reach out to you on the Slack and ask you a few things about this version 2 and the dead ends you hit while you were going in version 1, because there's some cool stuff that you were talking about.
Yeah, we'll be happy to get into more detail with that.
Cool. All right. So for everyone's knowledge, I was just looking through the Model Gone Rogue stories. There was a funny one that came up. Somebody talked about, so the question was, do you have any Model Gone Rogue stories? And let me read you the answer. And I'm just going to say, I don't know why they say that software engineers, data scientists don't follow directions, because look at this. My plan, all right, remember the question, do you have any Model Gone Rogue stories? My plan was to have one cat. I felt bad for my cat because she would stare outside the window and stand by the patio door looking at the view of the grass and trees. I started to let her go outside. She would go out in the morning and meow for me to let her. I got to pull myself together. She would meow for me to let her in at various points during the day. Soon, she started to look swollen. She was pregnant. Near the due date, I told my cousin she could have one of the little kittens. The litter was small. She had 2 little kittens, but one did not survive. My cat, Maxine, was so protective of her little unexpected kitten, I couldn't bear to tear them apart. 1 year later, I happily have 2 close and amazing cat babies. That's the model gone rogue story for you. All right. Next up, we've got Ben. Ben, I'm gonna try to pull myself together but I know that I've seen a sneak peek of your slides, so I think it's gonna be hard for me not to continue laughing with some of the slides that you have going on. Now, whoever wrote that cat story, please reach out to me. You're gonna get some swag. I also am going to share another model gone rogue story after Ben. And then we're going to vote after Joe on the best lightning talks, the best talks, and give away all the extra swag that we've got. But for now, Ben works at Databricks, all around badass, wrote a book on machine learning. You should probably go check it out. We try and get him on the MLOps community as much as possible because he is a wealth of wisdom. I'm handing it over to you, Ben.
Yeah, thanks, man. It's good to see you again.
Did you write the cat story?
I did not. I kind of wish I did. If I did, it probably would have ended up being a little bit more ridiculous, though. But which is much like this talk that you just introduced. So we're going to have a little bit of fun here. Who I am, Demetrios introduced me briefly. Yeah, I work at Databricks. I've been there for about 4 years. Used to be a data scientist. I've done a lot of stuff with personal projects that I've done in my career at companies, but also over the last 4 years have helped countless companies try to make sense out of data engineering, data science, and feature stores, actually, which is one of the reasons that we're going to be talking about today. And we're going to do this talk. I'm going to present a thesis, which is kind of ridiculous. There's going to be a lot of text that are going to be on these slides. You can review them later if you want to read through them, but they're meant to be funny. So our thesis is an ML project developed with entirely self-contained feature engineering, which is usually what we have with pipelines, isolates incredibly useful work within its pipeline and within that deployed production pipeline. An island is isolated from other parts of land because it's an island and it's surrounded by water. So we should build our ML infrastructure more like Tennessee. Now, this might get a little bit strange, but we'll go through this thesis and explain why I'm talking about it in this way. So this is Hawaii. It's an island. And there's a lot of really cool stuff there. Like really cool stuff. It's a great place to visit, but it's really known for being kind of hard to get to. It's pretty far away and you can't really drive there. But people do go there, typically on ships or airplanes. And we also move cargo to there via ships and airplanes. Now, this is Tennessee. Tennessee is, from what I understand, it's not an island. And there's a lot of cool stuff there, I think. I've been there a couple of times, but can't really validate much of that. But one of the things that Tennessee is also known for, and it's not a particularly well-known fun fact, but it has the highest concentration of extremely large warehouses on the planet. And there's a reason for that. And it's because it's pretty easy to get there, sort of centrally located in North America. And it's really easy to get things to and from there. You can use things like trains, which are really hard, from what I understand, to go over the Pacific Ocean to get to Hawaii. And you can fly stuff there as well, but it's kind of expensive to fly things there. So that's it for the analogy so far. But what I wanted to bring this up for is because a lot of ML projects and things that we do with data are kind of like being on an island. The data science team / ML team is at many companies is sort of isolated as if it's in Hawaii, and getting requirements can be like, we're receiving messages in a bottle cast off from the mainland saying, hey, data science team, we need this solved. Can you just go and do this? So that insulated aspect of work means that a lot of the feature engineering that's done is done separate from the data engineering team. That could be because hypothesis that we're trying to vet in utilizing for an application, the data could be incredibly challenging to get, very expensive, and it's just time consuming to write all that ETL. And because these ML projects are kind of like an island, and actually more like an archipelago, each project could be its own island that you may not be using or defining the exact same features that your peer is who's working on a different project. It may be that you're trying to use the same data in the same manner and doing the same calculations, but it doesn't actually turn out to be that way. So in this use case that I have on the slide here, this actually is a real world thing. The metrics that I'm going to show in the next slide are not real, but this actually happened at a company that I worked at before. We had about a dozen different products in the ML team and throughout BI, where we were all using the profit feature, and everybody had a different definition for it. Nobody was using what finance was using because it just wasn't in the data warehouse. So each of these projects calculated in a different way, and we end up getting these radically different numbers, and we're using these numbers in models. So when we start doing one of the most important aspects of productionizing our ML models, which is attribution analysis and evaluating how much business impact our work is actually having, there's no way that we could actually do that accurately. And one of the reasons why this is so challenging is because in an ML pipeline, a lot of the infrastructure and frameworks that we use actually force us to embed this transformation logic within a pipeline, deploy it to production, hope that everything goes well, collect data that we can, but it's really hard for other projects to use that code without introducing incredible complexity to other projects. And yes, we can create a framework for this. We can build abstraction on top of data transformation tasks, and we can maintain and own a ton of infrastructure. It always sounds like a good idea when people start out doing that, and then you have to maintain it. And as it grows over time, you end up with buyer's remorse, and you really wish that you hadn't done that. I've actually lived through that. It's pretty painful. But this infrastructure that you build with a custom framework, all you're doing is just bridging. So you're making it so that it's easy for project A to access some transformation that project C built, and then cobble all of this together. But it's not truly a centralized resource of persisted data and an online component associated with that. Now, one thing that we always talk about, anytime that somebody's talking from a vendor, we always see this chart. So I figured I'd put it in this presentation. These numbers are totally made up. I just have seen this particular pie chart probably 1,000 times on different blog posts and in presentations. So I figured I'd do my own. But really, the messaging of what this is we spend a lot of time as data scientists and ML engineers with data, manipulating it, transforming it, doing things with it to solve a problem, throwing it away. There's a lot of things that we spend time on just getting a feature vector ready for an ML algorithm or creating a feature data set that we can use for analytics or statistical inference. And because our time is spent so much on that part of ML engineering, we don't have a lot of time for that other phase. So let's pretend that we are actually doing an ML project. We spent a bunch of months on creating this evaluation of whether a user is going to click on an ad or not. And part of this framework that we need to create for solving this problem, we need to do some point in time joins, which are kind of tricky to write yourself manually. But part of this join is taking a bunch of information about ads and about users, and then we're getting a stream of data coming in saying, did they click on the ad or not? So we need this data that's coalesced in order for not only for training to happen, but also at inference time. So this is kind of the feature store model. But what we ended up doing in isolation, because we're all living in Hawaii doing this, we created an ML pipeline that compartmentalized all of this data manipulation into its pipeline. And inevitably, anybody that's been doing data science for a while, you're going to have an executive at some point saying, hey, how much money is this making us? And the response to that, unfortunately for our use case here, is we just had an intern start. Chris, welcome to the team. And his first task that's given is to answer this problem. And after looking through how to actually solve this and digging through the data and realizing that I actually need the data from the pipeline. I need that logic from within that project. And what Chris doesn't know, what the rest of the team knows, is that it was a massive undertaking to create that pipeline in the first place and to write all that feature engineering code. And they were doing a large construction project effectively in code. And unfortunately, Chris is kind of set up like this. It's not really well equipped to go through all of that code. And what he ends up having to do is realizing that he's not in Hawaii with the rest of the team. He's over in Guam. And he's even further from where any of the data is and any of the core attributes that he needs to collect in order to answer this business problem. So he ends up reverse engineering everything that they built. He has to learn a new language. It's all written in Scala on Spark. And then he has to rewrite basically that logic in SQL and use a bunch of tools to do that analysis to say, it is creating this percentage of lift with this. And this is what my analysis of the A/B tests have shown. So we can use a feature store instead, which is basically like Tennessee. Now for this use case that we're going through, that streaming data that's coming in, the raw clickstream data, we have an impression datetime. This is something that will be used for that point in time join because the ad is shown at some particular time. We want to know what whether somebody has clicked on it and what the state of the user data and the click data was at that time that the impression was shown. So we have this information about ads and what the relevance is to particular categories. And then we have data about our users, which is a slowly changing dimension. It's getting merged and updated periodically throughout the day as people are interacting with the platform. So what we could do is we can create in the Databricks feature store, we can create a feature table. We'll name it based on the database and table name. And we're going to give it the actual construction logic as that data frame. So whatever code we had to write in order to get data from sources and materialize something in memory, we can register that in the feature store, and it will allow us to periodically update it. We can schedule that to just update asynchronously, and we can also publish to an online feature store as well. And when we want to create this full data set that emulates a particular pipeline utilization of this data to solve this use case, we define it by saying these are the tables that we're going to be using to satisfy this join for basically the offline static data or the slowly changing data. And then we're also going to join it to the raw clickstream data, which is at the bottom here. And we want to use it for training, we just load the data frame. We want to use it for analysis. That last line of code in there is the same thing we're going to use. And that'll generate and materialize that data set for any use case that we need. So the TL and DR of this entire analogy that I've been talking about is this slide. And what a feature store that is fully integrated into an analytics platform can give you and why it's so important. Because that operationalizing, remember back to the pie chart that we were showing, that little sliver of information that most projects don't get enough time to devote to that, or you do it post hoc, like well after it's already in production, you're scrambling to get everything going. It's a lot of rework that you'd have to do without a feature store, and enabling stuff like drift monitoring of your features, doing analysis of correlation for, hey, the model is predicting this thing. I need to know what features are driving that. And I need to know how to actually change reality in order to get better results in the future. And general model explainability for launching something that's going into the hands of customers. That's something that we really want to understand why that model is behaving the way it is. And then all of the reporting and analysis. When we were talking about attribution modeling earlier, being able to tell on anything that we're releasing to the business why it works is very important, but the business really cares about how much money is this making us, whether that's in cost savings due to it's efficiently automating something that the business is otherwise spending a lot of time on, or it's just directly driving sales. Being able to give that number in a very rapid way and analyze the state of the data going in and coming out of the model is incredibly critical. So to wrap up the analogy, if we're talking about this Tennessee location of data, it really is just roads leading to there. And if our ML project that we're talking about is in North Carolina, we can do that attribution modeling and BI analysis relatively easily, because we're all just pointing to that centralized, locational warehouse. And when we're doing inference, we're doing prediction, we're doing retraining, and just general analysis of the business in general, having that single source of truth that everybody can align on and say, this is where our data is. This is what we're all going to agree on is the state of the world. This just makes it that much simpler. So yeah, in conclusion, let's be more like Tennessee with using feature stores for not just model training and inference, but also for all of the other myriad activities that are around and surrounding productionized ML solutions. So a little bit of shameless promotion. If you want to check out more about Databricks Feature Store and all of the exciting features that we are currently releasing right now and stuff that's going to be on the roadmap over the next year or two, the team is working really hard and doing some great work. Check it out. Just search Databricks Feature Store. You'll find out a lot of information. And the other part of the shameless promotion, I did write a book on MLOps. And yes, there are dogs in it and a lot of jokes. Check it out. It's going to go into production, I think, in end of April, early May. The print copies will ship out. And thanks for having me. And if anybody has any questions, yeah, let's do it.
Poor Chris. Poor Chris. Oh, he had to go to Guam. I've heard Guam's nice, though. I'll tell you that much.
There's a really big airstrip there. I've been there a couple of times on the Navy side of it. I don't know what the other part of it is, but yeah, lots of aircraft.
Which is something else I just realized that I forgot to mention about Ben. He spent 10 years in the Navy.
I did.
So that's pretty incredible too. Thank you, man. Awesome stuff. And please share the slides with us in Slack, because there were so many jokes that I missed when you pressed forward just fast enough so that I couldn't read all of it.
So I know that's the meta joke.
Yeah,
the meta joke is that there wasn't time to read them all.
I can only believe there's a lot of good Easter eggs on there. So that's it. That was awesome. That was really good. And I'm gonna steal that analogy, but I will give you proper attribution sometimes.
Oh, you don't need to. You could just own it, man. It's fine.
It's great. Tennessee. I never thought that I would look up to Tennessee so much. So there we go. We're going to keep moving. We've got 2 more talks, and one of them, our next guest, is Joe Reese, who is another friend of the MLOps community. I convinced him to come on here, and he is writing a book. When's the book going to be out, man? Fundamentals of Data Engineering, right?
Yeah, this summer. Yeah, data engineering. Yep. So
yeah,
joining
I'm
a
excited.
fellow author with Ben before. That's cool. You wrote a book. That's awesome. So yeah. Thanks. I'm glad you're excited. I hope everyone's excited. We'll talk about that. So
cool. Well, I don't want to take up more time because I know we're running short on it. Okay. I'm just going to let you go, Joe. Okay. For everybody that doesn't know Joe, you're going to find out who he is right now, real fast.
Assuming my sides work. 1 second here. Okay.
Nice. There we go.
Cool. We good? All right. Cool. Let me set my timer here. And if there's noise, I'm having furniture delivered upstairs as we speak. So sorry, can't plan that. Anyway, data engineering life cycle. Let's talk about this. Who's heard of life cycles for data? Just kind of show of hands. So anyway, that's what we're going to talk about specifically for data engineering. I think there's also a life cycle for machine learning, but we'll talk about data engineering. So why should you care? Well, I mean, you work with data, therefore you depend on data. But right now, there's some really big trends happening in the data industry. We're seeing simplification and abstraction of data tooling and practices.
Everything that was hard, 10 years ago, 20 years ago is now very easy. There's probably a solution for everything. And so you don't need to think about low-level tooling and practices as much unless you're building these tools, in which case, thank you for, building these things and making everyone's life easier who use these tools. At the same time, data and ML engineering, I think we're starting to see more of a holistic focus on the journey of data and its use in data products versus sort of the Tennessee and Hawaii problem that Ben talked about in his last, in the last talk, where everything is sort of balkanized, right? Like everything is starting to flow a lot nicer. I'm just seeing integrations, between different life cycles. I would say data engineering and ML engineering, I think, of different life cycles, but they're starting to everything's starting to flow very harmoniously, right? And this is going back to source systems that generate data and so forth. I think people are a lot more aware of the life cycle than they used to be. And so, as Dimitros mentioned, I'm writing a book on data engineering. And I think one of the problems of writing a book right now is, how do you know what's not going to change over the next few years? Why dedicate yourself to writing a book if the material is going to be obsolete by the time it goes to print? And so, one of the things I was really thinking about around this time last year when I started writing The Fundamentals of Data Engineering, which is a book that's coming out in O'Reilly this summer, what's not going to change, right? What are the immutables? And so why should you care? I think life cycle is going to become more of a hot topic over the next few years. And I think it's very important that you understand the life cycle of data. So let's get into that. Who am I? Quick thing, I'm a recovering data scientist. I've worked in all sorts of data roles since the early 2000s, whether it's ML, software engineering, analytics, data engineering, et cetera, et cetera, et cetera. If there's data involved, I've probably done it. So right now I run Ternary Data. We're a data engineering consulting firm based in Salt Lake City, Utah. I also teach at the University of Utah and I do podcasts, conferences, blog, writing a book, as we talked about, and so forth. In my spare time, I rock climb and trail run and all that fun stuff. So this is kind of the generic data lifecycle. I took this from a Harvard Business Review. If you Google data lifecycle, you'll find countless images about it, right? I kind of like this one where it goes through, I think, some pretty universal steps that could apply to data engineering, machine learning, and so forth, right? So data needs to be generated, collected, processed, stored, managed, analyzed, visualized, and interpreted. I would say the last part of this, like analysis, visualization, and interpretation, this is a bit old school. A lot of the data lifecycle charts that you see don't take into account machine learning, for example, right? So it assumes that you're just doing kind of traditional data analysis and viz and interpretation. This still obviously occurs. It's still incredibly vital to data, but things have changed a bit, and I feel like in a lot of cases, the life cycle concepts haven't really caught up. But this gives you kind of an idea, right? And notice as a cycle, at number 8, it goes back to generation, because assumably there's a feedback loop with your data. It doesn't just stop at one particular place, unless it sucks, and then it should stop. But we'll get to that too. Cool. So the data engineering workflow, I kind of like to look at it as, data engineering sits between systems that generate data and then downstream use cases like data science and analytics. Really, the job of a data engineer should be to get raw data, process it, maybe create data models, which we'll talk about in a bit, then make these useful for data scientists and analysts. So a data model could be anything from, a star schema, for example, raw tables that would be used for analysis, data that could be used, for machine learning. It's debatable whether or not a data engineer works with feature stores. I would say that maybe they have a hand in this for sure, since they're generating the raw data or the data that will be used for these downstream use cases. But basically, you take raw data, do something with it, and make it useful for downstream users. That's the data engineering workflow. So let's talk about lifecycle. So we're generating data, we're ingesting it, transforming, and serving it. All along the way, you're storing it in some fashion. When I thought about things that weren't going to change, the life cycle came to mind. And this life cycle in particular came to mind. This shouldn't be that much of a revelation, but when you try and, I guess, parse out like what's not going to change, with data engineering, this is what I came up with. Systems need to generate data. It needs to be ingested somehow. Transformation, perhaps. I would say that transformations provide the ROI for data, And then you're going to find a way to serve it. And all along the way, you're storing it maybe in a data warehouse, a data lake, feature store file system, graph database, any number of storage systems, right? I think that, we're sort of in an embarrassment of riches in some sense, where the number of tools that you have all along this life cycle are just, there's so many of them. They're so awesome, and you're serving data for downstream use cases, machine learning, analytics, reporting, reverse ETL, and so forth. But what about the undercurrents? You keep seeing things like data management, data governance, data ops, architecture, orchestration, all these things sort of fitting in. You're like, where does all this stuff go? And security is a really big one, right? So, and along the way, I was kind of thinking, well, where would this go? If you were to put security somewhere, where does that go in the life cycle? And it's like, it kind of goes everywhere, frankly. Same with data management, ops, architecture, orchestration, software engineering, all these things undercut. I would say not just the data engineering lifecycle, but I could make an argument for any data lifecycle, including the machine learning lifecycle. So let's get into the undercurrents real quick. See how we're doing on time here, 3 minutes. So the undercurrents, this is, I think, some of the newer ideas, right? Like if you look at what's not going to change, these don't change. Security doesn't change. Because you have better tooling or more abstraction, security still is a consideration. I challenge anyone to tell me where security wouldn't be important in data. If you find it, let me know. I'd be willing to talk about that. So what security really means is essentially access control to data and systems at the end of the day. The systems that are part of the life cycle, or the data that moves along the life cycle. But security is the number one thing, because I don't care how fancy your systems are. If you don't have good security, it's all going to fall apart at some point. So the next is data management. You're hearing a lot of stuff about data governance, discoverability, definitions, accountability, modeling, and so forth. These were things I would say that were very enterprisey before. Like big companies would barely be doing this. And now all of a sudden there's tools and projects and companies devoted to making this accessible to all sorts of companies, startups, and so forth, right? So this is, I would say, another big idea. Data management is something I think you're going to just see a lot more over the next few years, as people start adopting these practices for real. So a really good book, if you wanted to read it, is the Data Management Book of Knowledge. It's a 600-page gigantic book all about data management, but it's actually pretty fascinating to read if you really wanted to dig into sort of the underpinnings of data management. I thought it would be boring. I found like data governance is actually a pretty exciting topic. So hopefully Demetrios doesn't pull the plug on my talk now. Data ops. So ops in general, I think is another big undercurrent, right? So you're hearing a lot about observability. That's the big buzzword, I would say, of the 2020, 2021, and 2022. But automation, observability, monitoring, incident response. These are basically the principles of DevOps applied to data. So basically, what you're seeing, I think the other big trend is you're seeing just the principles of software engineering and DevOps being applied to data, whether that's machine learning or whether that's data engineering, same sorts of things, which is awesome because I think it represents sort of the maturity of where the industry is going. Data architecture, this is another big undercurrent of data engineering. Really what architecture is at the end of the day is trade-off analysis and how you design for agility and add value. That's really about it. There's no such thing as great architecture. There's only like least worst architecture. So, but architecture underpins a lot of how you're going to design your systems and build them. Do you build it for scalability and resilience, or are you sort of tacking on tools and hoping that they work together? So orchestration sort of, I think, undercuts a lot of things as well, right? Coordinating workflows, scheduling tasks and jobs, and so forth. Orchestration, there's a lot of action in this space, obviously, with the, Airflow kicked this off. I think democratized orchestration tools, and I have Dagster Prefect and lots of other projects coming down the pipe. And then software engineering too. I mean, writing good code, I think, is something that is a bit underrated, frankly, and when you get into data. So, knowing good programming skills, knowing how to test and debug, and knowing the general software design patterns go a long way. But again, all these things undercut data engineering. I can't think of a stage in the data engineering lifecycle where these aren't applicable. So really the big idea is, again, it's just, think of lifecycle. Lifecycle is really important, whether you're talking about machine learning, which I know this conference is mostly dedicated to, or data engineering. And so that's, I think it's going to be the big, sort of the big trend over the next few years is really lifecycle management. So shameless plug for my book, Fundamentals of Data Engineering. It's available as an early release on O'Reilly.com, raw and unedited. It's not finished yet, but at least you can get some ideas. There are chapters available now. It's coming out this summer. So if you have questions, drop them in Slack. And if you need to get a hold of me, here's how you do that. So thanks. I think I'm right at time, actually. So
nicely done. I love it when that happens. Then I can
bet you do.
goes over time. There are some people asking if you can repeat the name of that book you mentioned. The one.
Yeah, the name of
Data
book of Data Management Book of Knowledge. Very riveting title. I think it was written by a committee too, so take that with a grain of salt. But I would say that it has a lot of big ideas in there. That it's a good reference manual for sure. I read it probably every week. So
oh wow,
because I live an exciting life. So
yeah.
But,
excellent.
Yeah.
Right on. Well, for more questions, get at Joe in Slack. He's there. And follow him on LinkedIn. Watch his YouTube channel, Ternary Data. There's all kinds of great podcasts that he does. And we're finishing. This is our last talk. Before we finish, I want to remind you all that we're going to be giving away awards after this talk from Vitaly. And so there is still a chance to get some swag. In case you did not get swag, basically you just need to chat in Slack right now and you'll probably get that. Ask Joe a few questions. That'll probably give you some swag. But Vitaly, I'm excited to hear about you. I just want to know, you're at Better right now. Were you there when Eric, the former speaker, was on? Did you guys cross paths?
Yeah, we did for like 2 months, I think, or something like that. So.
Oh, all right, cool. Very cool.
I know.
Nice. Yes, nice. All right, man. Well, I'm gonna let you take over, and you're gonna bring us home.
Yeah.
So land this plane.
Yeah. Thank you. Thank you. Let's see. So I'm gonna start my timer. Start my slideshow. All right. So my name is Vitaly. I'm a software engineer at Better. So I'm going to be talking about how we used Feast in a ranking system. So I'm going to go with some concept around Feast and ranking in general. And I'm going to talk about lead scoring, which is the ranking system that we've implemented, and kind of where Feast fits into this architecture and kind of some things to consider. All right, so real quick, I think some people know about Feast, but from my point of view, when we were thinking about this, is we have several models, and they are dependent on some feature vector. And these feature vectors, they represent some entity usually. So in our case, in a ranking system, we're ranking leads. In other cases, you might have a relationship where different entities, for example, in a recommender system, have like customers relationship with like items, right? So, but in any case, we have features coming from different places. So in this case, feature view is a term, so is entities in Feast, and feature views are just different groupings of feature sets. And multiple feature views usually comprise of like the feature vector that the model depends on. And there's many different reasons to maybe group these features, but one almost mandatory reason is because they have different sources. So some can come from, I don't know, Excel sheets, some can be S3, Snowflake, and they can have multiple data sources, like in this diagram shown here, Snowflake or Kafka, or both. And if everything kind of works together and syncs correctly, everything syncs into this online store. And then we can use this online store for low latency feature retrieval and in the production system. So that's kind of very high level view of why we needed Feast. So now switching topics a little bit, going to ranking. So ranking models and problems are super vast. There's tons of them. And there is kind of, I'm going to be talking about lead scoring, but there's tons of other ones. But one, I probably cannot generalize this for all ranking systems, but one important question to ask from an architectural standpoint is, can you score the entity by itself and then later just push that score over to some queue of scores? Or are you thinking of ranking as like, is my list of stuff ranked well, right? So this comes into play of what kind of ranking algorithm you're going to pick. So in our case, we used pointwise. So this made it easy for us to look up something, score it, push it to some other queue of scores, or you would have to think of your whole list of entities as one thing that you're trying to predict on, right? And that's an important question of how you're going to do feature retrieval and how you're going to set up your architecture. So now a little bit about lead scoring. So real quick, a lead is not your customer yet, but you'd love them to be your customer. So you reach out to them and then some way increase conversion or some perceived value. And a little bit about our leads. We ingest leads throughout the day, I don't know, consistently throughout the day. You could say leads may be interacting with your product. You might have more information of them. So there's many different data sources. And another important thing is with time, leads are less likely to convert without some interaction. So in this sense, there's some decay, time decay. And that's more of an assumption that you might have to prove, but it's not a crazy assumption, I think. All right, so where does Feast and a feature store come in? So we have stuff that to maintain this list. So you're potentially interacting with the same entity many, many times, or the same entity sets many, many times. And not only are you interacting with them many times because you have to rank, re-rank, and also, but your features are potentially upgrading, updating continuously as well. So that's kind of the complexity there. And yeah, so let's break down that interaction. So in our case, we have new entities. We are updating features for the existing entities because they're interacting with stuff. And we have a decay function. As I said, if there's over time no interaction, then potentially that means a different score. So what this means is every time you predict, you have a different, potentially a different like ranking. So that's important as well. All right, so jumping into our kind of setup, I'll talk a little bit more about, so let me just kind of break down the systems, and then I'll break down kind of the life cycle of the lead coming in and where Feast really helps us. All right, so I think if you take out the right side of this whole diagram, you kind of see like a good platform, data platform. We have stuff coming in, a bunch of data sources, and coming into an offline store, and there's probably reporting systems on top of that as well. So our offline store at the moment consists of S3 sources, and Redshift we use as our data warehouse, and we use dbt to manage data models and also our like training and prediction data sets, which we really like dbt as well. So, and then on this side of thing, on the bottom is kind of what Feast helps us glue together. And yeah, it's great. So it helps us materialize things from our offline store to our online store, which we use Redis. And it also lets us keep track of certain business logic as well. For example, in our case, a lead is not a lead after 48 hours. So that makes it easy to, from a just maintaining data points perspective, to expire the whole entity and its feature vectors after 48 hours. And that makes it nice in Redis because you don't have too many things to look up or to manage. Kind of cleans itself. And then on the top right is kind of like the lead scoring stuff. So let me break down the kind of different ingestion patterns and features. So the very first thing, right, I said that we have a new lead. It's important to get it scored. So we ingest it right away from a streaming process. We have a lead scoring service that's going to validate the lead, transform it. And at this point, we can score it. So this is where we pass off that score to a queue system, call queue system. But at the same time, we might have to interact with this entity right away, meaning in a minute or so, because it might be part of a re-ranking function as well. So at this point, we ingest this directly into Feast. Direct ingestion is supported for Redis, so this makes it easy. And it's there, so it's living with some features. At the same time, and potentially in the background, we have new features for that lead coming in. And this is, of course, a little bit more time-consuming process, but we can reuse the ETL and all the like data platform infrastructure that we already have that may have already transformed a bunch of features for us and materialize that periodically into our Redis online store. There's two benefits to this and some downsides. One benefit is that you can have some redundancy. So even if we miss some things, it's all good. We can still catch up with our normal ETL processes. We also can reuse a lot of processes to ingest new features into the online store without having to set up too many streaming features and crazy transformations and things like that. And at the same time, right, we have time decay and we have updated features. So the call queue service that knows that we have stuff to call is going to reach out and say, hey, give us the latest and greatest scores and we'll re-rank them. So it all kind of syncs together. And what helped us really glue this whole pipeline is Feast, because it can help us manage these many different data sources, many different feature views, and kind of keep that business logic for leads. So my last slide here. So a couple of things to consider. Again, I think one thing I pointed out, there's probably a different architecture to consider if you're going to go for the learn to rank approach, where you really have to think about the relative ranking of things. In our case, we can score a single thing by itself and then kind of manage those scores in different sequences. Quick, like kind of silly question, but something that might come into play is like, well, in the system, what's the difference between position 5 and 10? In our case, it doesn't really matter too much. In some cases, it might mean that the person's viewing it on the front page or on the second page, right? So that might be really important and might lean towards more of a learn to rank approach. And then, yeah, for Redis is great for lookups, but it's important to understand what we're looking up. In our case, we were looking up an entity by itself or a set of entities for re-ranking, but it never was more than 10,000 things that we're re-ranking at a time because, well, leads expire, so we don't have to maintain those anymore. And then the other thing is, yeah, I guess we just don't have that many leads compared to, or that's the problem set. I can imagine if you're trying to rank 1 million things, that might not come into might not be great, but maybe you could try different approaches where you can filter out using pointwise and kind of like, really think about, do you really need to rank the whole 1 million things at from a client perspective, or user perspective. So that's kind of some things to consider. Yeah, and quick shout out to Danny from the Feast and Tecton team that's been kind of holding my hand through this whole understanding of how to integrate Feast into our setup. So thank you. All right, that's all I got. Thank you so much. And let me know if you have any questions.
Amazing. All right, I got to request my video to be turned on. I got canceled again. There we go. I'm back up. They can't get rid of me just yet. Vitaly, thanks, man. That was brilliant. I appreciate it. And you brought us home. We are now done with the Apply conference, and I get to give away some presents. I get to give away the last little bit of swag that we've got. So, you all ready for some awards? I hope. It's going to be the last little bit. Boom. Best selfie goes to this guy, just because I think this is a hilarious photo. Whoever you are, reach out to me. I don't know the names on the selfies because if you look at Photo Booth, the gallery, you don't get names, but there's been some good ones. This was also a great one. If you're still on here, whoever you are with your dog, reach out to me. We'll give you some swag. All right, so we got the best selfie award. We've also got the best talk. Who did this go to? I threw in there the link in Slack for you to vote, and it looks like people were saying that their favorite 30-minute talk, just by a hair, that was Stefan at his incredibly fast-paced talk. He was able to condense a 60-minute talk into a 30-minute talk. And so Stefan, reach out to me, get a hold of me, and I'll give you some swag. The next one is, what is the best lightning talk? And what it looked like, we only got a few votes on this. So it was Ben, because of his Hawaii, and I think because of good old, who was it? Chad or Phil? I can't remember now, but that poor data scientist intern that they had. So Ben, you get some swag, and then let's keep it rolling. What's the next award? Most active in Slack. This one goes to Mr. Daniel, Public Daniel, except I'm going to veto this one because he wrote me once when we put out all the MLOps community merch, and he was like, oh, I want one of these, but I'm too cheap to buy it. So now you're not getting swag. You're getting some swag taken away from you. Go buy some merch, and then I'll give you all the swag you want. And so since Daniel doesn't win, who gets it? Well, Team Ramp, if you all are still here, you got the Slack takeover. So everyone from Team Ramp, you all just came in and you introduced yourself and you took over Slack. So you all get some swag and reach out to me and I will get you in contact with that. All right. And everyone should know that there is another one of these happening in May. In case you didn't hear, in May, we've got another Apply conference, and hopefully I will get invited back to host it again. I didn't say anything here that might potentially have gotten me discontinued. And the other thing is, everything that you saw here, if you want to go back and watch Stefan's talk at half speed so it sounds normal, you can do that because everything is on demand. That is it. I will also mention that, it is in my contract. I am contractually obliged to say that Tekton is hiring. I forgot about that one and I needed to squeeze that in. So if you're looking for a job, go reach out to the Tekton guys. I think you saw a lot of them on here today. And that's all we got. I hope you all enjoyed it. Give us feedback. Let us know what you thought. We would love to hear from you. And so we're going to be sending feedback forms to you via email, or we're also dropping it in the chat right now. So please, we want to make this better. And if you liked or didn't like something, let us know, because that's how it can get better for the next time. That's all we got, y'all. Thanks. It's been great. Really appreciate it. Now I got to get to bed because it is late over here in Germany.